Welcome to APEC. It's November 25th, and I am your moderator, Tim Ventura. First, I want to thank everybody for joining us on today's call, along with everybody who is watching us on YouTube. So I want to give you some updates. We have some amazing presentations happening today. Today is also APEC's third birthday. So let's give ourselves a big hand. We have made it 3 years. We are the community center for emerging propulsion. We have had all of the biggest names, and we are super excited to be serving you, the community, and just keeping you updated and informed on all of this research. And there is so much happening. So today, Dr. Salvatore Pais and John Brandenburg will be discussing the Superforce. We recorded that earlier in the week because Dr. Pais isn't able to actually be with us today. We're going to play that recording, which was made for APEC. Mitch Randall is going to be explaining passive radar for UAP tracking. That is a really exciting technology. And Hugh Deasy is going to be explaining his research into prime numbers along with applications for warp drives and breakthrough propulsion. We are also anticipating Dr. Jack Sarfatti, who will be discussing UAP Physics. So again, this is our third birthday. We are super excited. We're going to be doing some ad hoc presentations and celebration during LAD time. We've got a lot going on. Couple of quick updates before we begin. Today's event is on StreamYard, broadcasting through the Alt Propulsion YouTube channel, as well as Alien Scientist and Bernie's channel and several others. If you haven't subscribed, please do so now. You can go to our website at altpropulsion.com. You can watch any of our videos there. We've got replays, details, and speaker info there. You can also find your way to our YouTube site and subscribe to that as well. So without any further ado, I want to introduce our first presenter. Hugh Deasy is going to be discussing prime numbers, warp drives, breakthrough propulsion. He has insights into prime numbers based on computer program analysis that he's been using to investigate features of prime numbers. He believes that this research has led to a fundamental discovery about prime numbers that could potentially be related to Searl's law of the squares. And actually, this came out of a presentation that we did last month. And he saw that and he said, this ties into my work. And so he reached out to us to do a presentation. I'm so excited to have him. He also believes this has, obviously, if it's related to Searl, propulsion and energy generation applications. He's also going to be discussing a competing idea to the IVO quantum drive, which I believe is currently in space, waiting to begin tests. And he's going to be offering some suggestions for an avenue of design for a hyperspace propulsion system. So I am going to bring him on. Hugh, thank you so much for joining us, sir. Let me unmute you. Wonderful.
Right.
Thank you. Well,
okay, then, if you would be so kind as to put up my presentation.
I will. And, I want to let everyone in the audience know you are joining us during a business trip to China. So it is the wee hours of the morning your time. Thank you so much for taking the time, not only to put these together, but to stay up in the middle of the night. You said you'll be home in Germany in I think about a couple of weeks, but right now,
yes, in 3 weeks.
It is the middle of the night. So, sir, thank you. I will take myself out and just let me know if you have any trouble, and I can put the other slide deck up as well.
Okay. All right, then. So here we have it. Prime numbers, a new feature by myself. And let's just go on to the first really business end of the slides, which is just an overview. And the discovery is of a new regularity. Some people have noticed something similar. I'll discuss that, but they're not exactly the same as mine. So mine is, I think, completely new. And using computer programs, this is what gave me the insight into it. I was investigating certain trends in prime numbers, and lo and behold, this feature popped out. And indeed, let's have a look at the next slide. Yes, this is just the general introduction. As a theoretical physicist and astronomer, I had experience in mathematics, and as part of that, an investigation into trends in prime numbers, I wrote some programs to investigate these trends. Now, my first effort was a simple fitting of curves to prime numbers up to a few million. Very simple stuff. And I'll just show the results of that in the next slide. And that is two cases. The red is up to 1,000 prime numbers. This is the residuals of a quadratic fit, just using n squared plus an squared plus b n squared plus c, etc., optimized to different numbers of primes, and then you get the residuals, and you plot them out, and you find that it's self-similar. But this is actually nothing new. This is all part of the Gaussian and Riemannian distributions. So that was nothing really new there. But in the next investigation, it was something new. It was looking at the prime number endings. Now, apart from 2 and 5, 2 and 5 are the exceptions in the decimal system because they both divide into 10. So that means that they, after making a brief appearance, then they fade away from the endings of prime numbers. There's only two of them that end in 2 and 5, namely 2 and 5, but all other prime numbers end in 1, 3, 7, or 9. If you look at them all, 29, 37, blah, blah, you'll invariably find they end in 1, 3, 7, or 9. Obviously, it couldn't end in an even number because that would divide by 2. And similarly, you can't have anything ending in 5 because that would be divisible by 5. And the innovation was to look at increments. That is, if you're on the nth prime number, you see what it ends in. Let's say it ends in a 7. Then the increment is the next prime number. Say you have 17 and 19 is the next one. Then the increment to that is 2. And then you would add that 2 onto the counter for 7. You'll see an example of this in the next slide, which shows my program in action, as it were. You just follow it along these colored lines. Now the green lines show the increments, the green boxes. And what I have here is a table with the number of the prime number. That is just 1, 2 is the first prime number, 3 is number 2, 5 is number 3, etc. So that's using that system. And then you have the actual prime number, and then you have the ending, what it ends in. Then you have increments, the increment to the next prime number, and then you have the 4 summation indices, as it were, and we'll see how they are updated as we go along. Just first of all, for 11 there, you follow the line across to 1, it ends in a 1, and the increment to 13 is a 2, etc. I don't have it all in one line, unfortunately, so we have a kink in it there. So goes the increment 2, and this 2 is then added to the total for 1, with a 1 ending. That is now 2. It was 0, it's 2. Similarly for 13, it ends in a 3. The increment to 17 is 4. And then we add that on to the total for the 3 ending. And that was 2 and now becomes 6 when you add the 4 to it. And similarly with 7, you go over and that's ending in 7. Increment to 19 is 2. And that goes to increase the total for 7 by 2. And we can do similar right down to the third last one there, 61. It ends in a 1. The increment to 67 is 6. And that goes on, you add 6 to the total for 1, which then goes from 10 to 16. And 67, ending in 7, increment to 71 is 4. And then you add on 4 to the total for 7 and you get 16 to 20. Anyway, that I've checked that up until several million just to be sure there were no glitches or whatever in it. Because there was one bug initially and I ironed that out and now it seems to be working perfectly. Anyway, so what you do is you plot the results from that. If you get these 4, tote 1, tote 2, tote 7, tote 9, that's what we'll be plotting in the next few plots. So that's what we'll see here. For example, up until a few hundred, you might think that nothing unusual was happening because you see that the total for 1 is wandering all over the place, the total for 3 is wandering, and the total for 7, etc. So they're all seem to be doing some sort of random walk around it. Now, what you have again is at any point there's a prime number. For example, at the last one here is 500, number 500, and that was made up of contributions. A bit less of a contribution from 7. Prime number is ending in 7, incrementing, and then the other 3 are more or less equal. Let's go on to the next one. But now if you go, lo and behold, if you go from hundreds up until thousands, it's like the fog clears and the pixels, as it were, in a photograph, suddenly lets the actual underlying pattern appear. And here what we have is a very consistent trend where the contribution from 3 is the top and from 7 is the least in this incrementing from one to the next system. And if you even go up to 15 million, I've done this up to 300 million, etc. So it does become proportionately less. For example, in the last one, we had about 1/7 of the mean quarter prime number was the range of the variations, whereas if you go over to 15 million, it's now almost 1/8. It's between 1/7 and 1/8 of the total mean prime number that the variation range goes over. Now, what you can do to make it more, so it doesn't disappear and get lost in the wash of infinity, is to plot out the deviation from that quarter prime number. So you always subtract the data in the last curves, you just again, if you have here this in the center of that variation is a point which is the actual quarter prime. You subtract that then from that at every point, and for the particular prime number you're at, you don't use just the last prime number. You just use the corresponding prime number at each point, and then you get this nice spread of the lines. So even at 15 million, you see there are some minor kinks in the curves. So, but on average, it does show a nice straight line turning off towards infinity. Now, the other thing is you can look at either the 4 cases or 16 cases. And this was due to I discovered other workers in the field had discovered the first weird thing about these prime number increments. So they didn't look at the increments. What they did was they just looked at the actual the totaling up of the cases. One goes to an ending in 1 goes to an ending in 3, and then an ending in 1 goes to an ending in 7, an ending in 1 goes
Dr.
to an ending
Salvatore
in
Pais.
19. Sorry? What's happened there? Can you put my presentation? Oh, what happened to my presentation? Oh, there it is. And so what you have in their case, they looked at the 17 cases, 1 to 1, 3 to 3, 3 to 7, 3 to 9, 7 to 1, 7, etc., etc. So to be consistent in a comparison with their case, and by the way, they are Lemke and Soundara Jen. Let's go there. And anyway, in my case, splitting it up, you have the previous things that I was plotting was all the total in the last column here, which is the summation of the 4 individual components. So for the from 1 is composed of all from 1 to 1s, from 1 to 3s, from 1 to 7, from 1 to 9. And similarly, you find a very similar trends if you total up the columns. Now these are the other workers in the field who discovered that thing with the simple the toting. And what they're with Lemke and Soundara Arajan, that's a bit of a mouthful. I'm just going to say L and S from now on. And what you find, L and S discovered, they looked at the percentages of these increments, as it were, but increments, digital increments, in that one goes, the cases where 1 goes to 1, and 1 goes to 3, 1 goes to 7, 1 goes to 9. What you see here is along the diagonal, 1 to 1, 3 to 3, 7 to 7, 9 to 9. Those are all very low. They're the only cases in their tables ending in beginning with a 4%. In my case, it's also a case, but not quite as pronounced. But in my case, they're the only cases. Well, some of the only cases. One off diagonal case, with also starting with 5%. So what you see is similarities in the two tables, but they're not perfectly symmetrical. Another aspect is the summations of each from and to case are almost exactly 25%. As you see, in our case, that is not the case. We have massive deviations of up to 2 and 3% from almost 3% from, no, sorry, it's 1% on the order of 1%, but still this is massive compared to the almost non-existent deviations of L and S. And what you see is that we don't see exactly the same situation. For example, their largest case, the only case which is 25.00, is the from 7, whereas in our case, that's the lowest one. That's the lowest deviation. That's 23.799. That's the only 23, and it's much lower than the others. Whereas in the case of the 2.3, they have that as the largest, 25, and the 2.7 as the smallest, 24.9. But we see the exact opposite. We see 23.814, the lowest for 3, and the largest 2.7. Anyway, that all shows that though there are similarities in the tables, they're not always identical. And what you can do is you can look at the predominance, whether ours are more or greater than or theirs. So I just say ours or theirs. And you've got this thing auto comes out as a natural result, and you get a moat of a sort of a castle of theirs surrounded by a moat of ours in it. So there is a certain symmetry in there, but symmetry in asymmetry, as it were. And if you plot out the tables, this is something interesting that will become interesting later in comparison with Searl. You see here there's not really any great trend, but there is a sort of a grouping towards the center, though you might say. Whereas in their case, they don't have this grouping toward the center, but they have similar topologies. And if you compare the two, again, you see they have larger, ironically, they have larger individual deviations in the percentages, whereas their totals hardly vary at all. Whereas we have the opposite. We have large variations in the total, but not such huge variations in the individual components. What you see here is that the topology, for example, in blue there, you see that that's got a similar double kink in it, and the green you see has that hat feature in both of them. It's not perfect, but anyway, there is some similarity between the two of them. Sorry. Okay, so here we have, going over to comparison with Searl. Now what Searl, in his marvelous number table, you see this is just a wonderful thing. He takes the numbers from 1 to 16 and rearranges them, and the summation of every row is 34 and the columns are all 34. And what's more, the sub matrices all sum to 34 as well, and the diagonals. And there's all sorts of symmetries in it. For example, everyone going in the columns of the different colors, you find a 13, and a 21. For example, green is 1 plus 12, 13, and 15 plus 6, 21. Whereas red is 4 plus 9, 13, and 14 plus 7, 21. And you find that is the case for all columns, and then with the rows, it's 16 and 18. If you look at that, it's 16 and 18. You can do it out for yourselves there, and it's quite a fun thing to play with. And if we look at a comparison, the comparison for the Searl table, I decided I don't know if he did this himself, but what you do is you just, because he has some books on it, I confess I haven't gone through them in detail, but he did a lot of investigation of the properties of this table. But one other thing is to join 1 to 2, then 2 to 3, 3 to 4, 4 to 5, 6 to 7, 5 to 6, 6 to 7, etc. And what you get then is this pattern, which is, at first looks a bit chaotic, but when you look at it on its own, you find it has certain symmetries. The triangles are all beautifully symmetric, and you even get a star in the center. That could show that his systems are tending towards space propulsion because you have a star in it. But if you do the same, now what we did to make a comparison with our table, well, I noticed that he had his 4 table here, and we have our from to table. So I took the from to table with the percentages and I did a similar thing. I took the smallest percentage and then linked it to the second smallest, then to the third smallest, fourth smallest, and went around that way. And we see that we get something there. It's a bit chaotic compared to the beautiful mathematical purity of the Searl table, but if you see, we do have 2 lobes on these 2 large triangles, more or less, on the bottom left and top right hand points. And what Searl also has are these 2 nexus points, as I call them, these intersections right and left of the star. At the foot of the star, there are points where 4 different lines go through it, or you get 8 radians, an octagonal radiant, as it were. But in my case, you only have 1 6 radiant, and in that case, 2 of them are actually coming out from it. There's an actual point there. Whereas in his case, they're all intersecting by wonderful coincidence or wonderful beauty of the mathematics involved. Whereas here, with the prime numbers, it's also coming from mathematics, but it's slightly not quite as dramatic. The symmetry. The other thing is a swath. There's a swath going from top left to bottom right in both of them. You can see that theirs is placed a bit towards the center, whereas ours is a bit down towards the side. But again, there are those similarities. And who knows, maybe there is some input from the prime numbers to propulsion physics, just as Searl found that his table was used as a guide to constructing the relative sizes of his components in his system. And that then is the end of the prime number presentation. I'm bang on the button there. I just used 30 minutes of the hour on that one. Now I'm going to go over to the propulsion one. You could get up the propulsion. Thank you. And here we have propulsion by myself. And we're going to have a look at the Lorentz force, some progress theory simulations, gyroscopic, some experiments were done and agreed with the theory. I'll show a little video of the rig there, completely open. I'm completely sharing the results of my gyroscopic system. But with the centrifugal, I'm being a bit more coy, as it were, in that I'm going to show a video, but it's going to hide the business end of the rig. But what we have are more experiments and developments in Germany and in China. Also here I made some progress in that. And it's really the most likely to succeed because it's the easiest road to success. You can easily construct a more powerful centrifugal rig than the gyroscopic rig, for example. And going on to hyperspace travel, at the end I will make a brief mention of that, and we'll see where that leads. Okay. So, first of all, looking at the advantages of the Lorentz force, it's solid state. That's the wonderful thing about it compared to the other ones. You don't have any annoying moving parts shaking the thing to and fro. You just have a straightforward, either you've got propulsion or you don't. But it's the disadvantage is you have to put in a lot of power. So the power to force ratio is not so good. For example, with the IVO system, which is in the process of being tested in space at the moment, it's amazing. You know, it's the first ever test of a reactionless system in space. They're not calling it reactionless, of course. They say, oh, it's pure quantum reaction and all that. But when we come right down to it, it is simply a propulsion system where you have no propellant coming out the back. You just have an internal action, and that causes the satellite to raise up in a few seconds by 100 meters. That's what they're hoping to achieve. And if it's anything like what they saw on the ground, that's what they'll get. And it's great that they've achieved this, because they have now, as a company, they have developed their system and they're bringing it to test in space. It's just wonderful. And hopefully we will have, and that's actually been a spur to all those others working on reactionless propulsion systems to get them to work. Now I'm going to get a prototype made up here of one of the main ideas for the Lorentz force. Again, that, funny enough, it still isn't as good as the IVO one, though the centrifugal one will be as good. But again, looking at the different aspects here, with pulsing with many small units, you can get a good mean force. If you pulse between them, you can't just keep pulsing large currents into one because it would overheat. So you have to let it pause, and then you pulse another one and let that one pause, and so on. You can have about 100 small coils pulsing, and then that would give a large result, mean result. That's the idea behind that. And anyway, given the materials, it's easy to construct some test units. But for more money, you can construct a very special coil, which is much more efficient and gives a good ratio, force to power ratio, but still not up to the level of the IVO one. But if you go to cryogenics, it is, but I haven't yet gone to cryogenics. that would take more money to go to cryogenic. Anyway, just looking at an example of one case, 30 there's a flat wire of 35 millimeters by 1 millimeter. That's nice thin wafer, as it were, going along. And you have a coil made out of a special coil constructed from a spiral of 30 of those 35 millimeter wide flat wires. And if you put, normally that can take without problem 100 amps, but if you put 10 times that, the amperage in the wire for a short pulse, then you have, say, 1,500, 1,050 rather. That's easy because you can, for divisions, etc. And what you do is when you multiply that by 30, you find the total number of amp turns is 3.15 E4. And what the Lorentz force is roughly, a rule of thumb, is 10 to the minus 7 times amp turns, gives more or less the ballpark of the force. Now, in this case, it gave a bit too high. It gave 99 newtons, but the detailed simulation showed it was more like 9, so it was about 11 times greater than the actual simulated one, which is always very close to the actual found in tests. So, unfortunately, we would like to have the theoretical 10 to the minus 7 of current squared, but it doesn't work out like that in practice. We're a bit worse than that, as is so often the case in physics or in life in general. But with 60 units in a coil and subunits, this is one way to optimize it. You can use less wire in small subunits in a coil, and then you can have a sort of a granulated complete coil, and you get then 60 units, subunits, and you get 60 times that smaller force, 69. But because simulations have also showed that many subunits adjacent, the actual contribution from them goes down by a factor of 0.63 for 10 of them, spaced by about by 5 millimeters, etc. So that's where that 0.63 comes from. Anyway, what you get then is 240 newtons, and when you do it out, you need 11 kilowatts for that. And that's 0.03 newtons per watt. That's compared to 0.05 newtons per watt for the IVO system. But they've got something that actually gives more newtons per watt. But actually, we can get more concentrated force. For a very small coil, we can get hundreds of newtons, whereas they have to use multiple of their boxes, I believe. They can't get one box to produce huge amounts, which pulsing of a large current. But I don't know if that's the case, but I suspect it isn't from what I've read so far of their system. But you can do it with the Lorentz system. Anyway, each coil weighs 12 kilograms, and 100 of them, if you were to use that for pulsing, then you would have a huge weight of 1,200 kg. So that would be not very good for trying to have liftoff. But you could do it with, in principle, if you had cryogenics, but that's in the future. And now looking at the disadvantages, again, heating is your big bugbear here. If current is too high for too long, then the coil just heats up. This heating limits the force in the so-called poor man's version. That's the simple one, the simplest, which if you had some wire and some other components, you could easily build it up. That's what I call the poor man's version. But the optimal or the special coil is more or less needs a lot of money input there, for that's the rich man's version, as it were. So in the PMV, which is all I've been able to afford so far, but we're on the heel of this IVO pulse that went through the system. I'm now producing my first sort of rich man's prototype to try and get that up near to the level of the IVO one. But anyway, it's tricky to get all the add-ons and the permeability and the saturation field. That's another thing you have to look out for in the Lorentz system. That your field is too great, it can saturate certain elements of the system, and that leads to a lower force. Anyway, looking at cryogenic, you see that even without using superconducting, the problem with superconducting is it quenches very easily. You've had shutdowns of the LHC because somebody went near it with the giant magnets, which they're mobile or something, and then the whole thing collapsed, and they were down for a few months trying to salvage the system. And you see it also in going into one of these scanners. You're not allowed to bring in your mobiles or any megahertz type device in there, because that would simply be too much of a jiggering on the superconducting and would cause it to quench and collapse in of itself. But with cryogenics, with pure copper, you can get down. That's why they wrap superconductors in LHC and elsewhere in pure copper. But that's the next best thing to a superconductor. It loses up to 1,000 of its resistance. So it goes down to 1,000 at room temperature here, down to 3K, for example. You get 1,000 very pure copper. The graph shows increasing level of purity as you go downwards. RR 2000 means more or less a measure of the purity. Anyway, continuing with the cryogenics, looking at cryostats, they are very promising. They've now got ones that don't even need liquid helium or nitrogen, and they use pulse tube cryocoolers. But at the moment, their sample space, as it were, is only a few cc, a few cubic centimeters. So in order to be useful for the Lorentz force, they would need to have a larger sample container. So maybe in the future, when this technology is more developed, they may produce one with larger sample cases, and that would then allow decent sized Lorentz propulsor to be in there. Now, a quick and dirty way of testing it is just to fill a box with liquid helium, as was done for the NASICAL tests. NASICAL was one of the other Lorentz propulsion attempts, but unfortunately his conical coil didn't produce any result. I could have told him that because my simulations already showed that that sort of conical thing cannot produce any notable force. This should also, this should allow high pulse current test, pulses of current before the helium evaporates. So that would be a thing I could try in the future. Anyway, looking at the alternatives for this, for use of the Lorentz force, if you pump in more money initially, you get this special coil which has up to hundreds of newtons for relatively low power. As we saw, that means kilowatts instead of tens of kilowatts. But with a flat wire 3D printed one, now it's becoming cheaper. These flat wire 3D printed ones, you can get that for a bit less money than the old-fashioned multiple round wires of, say, 1 millimeter diameter, then cross section. Then you would have, say, 900 turns in that coil. Here we only have 30 of these flat wire coils, flat wires, which are equivalent to the 900 turn coil of the pure wire coil, of the normal wire coil. And anyway, you can use different versions also involving capacitors and magnetic fields, but it's not clear if they have the same. The beauty of the Lorentz force is one force. I scratch your back and you scratch mine, where one has the force, the true force of a corner, where one side of the corner is acting on the other, and the other returns the favor and acts on the first one. So they both pull each other up by their own bootstraps. That's how you do it in that case. Anyway, the summary: better to use this special coil because you get more power for your, force for your power, and with the flat wire and pulse system, you can more easily achieve this for less money than was needed before. Then, though it's harder to construct than the gyro or centrifugal propulsion systems, the solid state nature is still an attractive feature. So it would be nice to get this to work with an efficiency approaching that of the centrifugal sometime in the future, as you don't have that banging around photo activity. Anyway, let's go over to the next slide. Now, again, just looking at gyroscopic propulsion, stepping back and looking at the large view, that from time immemorial humans have dreamt of flight, and you have Icarus to Leonardo da Vinci, and here you have a Leonardo da Vinci sketch with multiple round moving components and some wing-like or propeller-like components, etc. So we have, with one of the main testers of the gyroscopic propulsion in the past, Sandy Kidd. He did a version with rotating, spinning gyros. On this, for example, you see it on the right. This light gray object is about half of the rig. It's symmetric about that. You can imagine that progressed to the other side as well, to the right, then you would have the full thing. So it's more or less like a Y-shaped system. And what you have is it goes inward. The spinning gyros move inward, and that causes the upward pulse of force. And what he has here is a balance where he has a weight, and it was without putting any input power into it, then it would just be balanced when I think this the balance was higher up, and then that sank down and the gyro system rose up. That was a great proof of concept of the system. And anyway, looking at some features of it, looking at his tests, I had some ideas for my gyro car. At first I thought of using normal symmetric gyros, but that gave almost no effect. So from centrifugal cases, I knew that you often get a better case with with just a singular weight rotating than with a solid disk rotating. So I switched from a disk to a solid rotating weight, to a rotating weight. And now I'm going to put up the first of my videos here. When I do that, Jim, can you allow me to put up the video of the...
Yeah. So which one do you want to do? Do you want to do? Is it
one on the extreme right? The one on the extreme right. The extreme right.
Let me see.
Yeah, there we are. Now there it is. It's moving along. And what you notice is it's rotating in the opposite way to a wheel on the car would move if it was moving. So that's not just moving like a wheel, but it's moving actually, and that's the exact correct direction you get. For example, if we go back to my presentation again, Tim, can you go back to the present? Thanks. And what you see here is, again, as I say, that's the weight rotates in the opposite, and this shows that it's indeed precession. If you do the old right-hand rule, it's the force of gravity going down and the rotor going out. Convention shows that it's if you use the right hand, you get the rotations give then the direction of the angular momentum, the angular velocity, as it were, and you do in the right hand the three-fingered rule to get the direction of the force, and then you see that if it's going in the direction opposite to a wheel, then it goes forward, and it shows that it's the right stuff. So that's what is in my rig, and what you could have would be that I also found that it was better with heavier weight going slowly than with a small weight going fast. This could be the way for a car, to have something like a 10 kilogram weight rotating. That could give some additional, it wouldn't be enough to propel the car on its own, but it would give a sort of a hybrid system where it would assist the petrol or the battery of the car, which is just driving a normal motor to push the wheels. And you could have these for a little extra power. You would have these giving probably a more efficient boost, as it were, but not enough to push the car on its own. So more tests are needed to optimize these systems. It could be that they find that with enough optimization, you could actually have a pure gyro car. But another variation is the upright system, which is the next video, which is the one you showed initially. That the second on the extreme left. I mean, so one of the extreme left here. You can put up that video, Jim. Yeah, there we are. So that is what we have here. This reminded me of one of your presenters a while back. I forget his name at the moment. Had a box. I was wondering if you had something like this in it. But here we have a pure
0.3 amps or so.
mover.
Watts. 1.3 watts.
And it's only using a 1.8 watts. So it's of course it's not producing much.
Going fairly steadily
motion,
forward.
It's fairly efficient.
It's low power or lower speed. I think
And
if
if
we
we-
had a higher weight and more power, then it would go forward also.
Exactly.
Thank you.
Thank you, Lee. And that's it. So if we go back to the presentation, then again, if you have smaller weights rotating at greater speed, it's possible that we haven't done all the tests on that yet. But this one already had a smaller weight than we were using in the gyro car, for example. But again, we have to look at the limits on that, what sort of force you get for the smaller one or the bigger one or whatever. So we need a lot more tests on this sort of system. And again, summarizing that, the horizontal system, it's good. It could, in principle, be used in space, and it's anyway going on because I don't have much time left. To the centrifugal propulsion, it's similar in that you have rotating systems or rotating weights, and you need to directionalize the force. Variations of radius doesn't work due to the Coriolis effect. So if you just vary 99% of patents in this area have a system where the old ballerina effect, where you pull in the arms and then you go quicker, and you find that the pure arm variation systems don't work because of the Coriolis effect. I'll show that in the next course. And this is the system of Provatidis. I actually did a very similar one to this. It was my first ever centrifugal rig, as it were. But to my great disappointment, it didn't go anywhere. And I looked into it and I found it was the Coriolis effect, which was causing the counter force there. And I believe Provatidis hasn't got his system to work either, because it's essentially the same as my one, producing a figure of 8. If you see here, this figure of 8 saddle type thing pointing upwards, he was hoping to get a net upward force. But unfortunately, you won't find it because this pure variation, the Coriolis, goes against centrifugal, if you do out the maths. But what did work was Thornton's system, for example. This is the final video of this lot. If you could put up that one, oh, you have that one up. Okay, so I'm going to. Oh no, I just the slide up there. Can you actually put up the video? Now you see he's going across the swimming pool, with just that paddle at the ready, but he's not actually using the paddle, just in case it gave a crazy force and he had to counter steer or something. But it remained quite a steady force. And this you see then an insight into the actual system. If you go back to the presentation, then I can show what was in that case. That was this sort of double rotor. Now, again, that's a variation on a rotor on the radius size variation. So it's not clear why his worked. But there must be some, I think there is another force. I'm looking into that, and I think I know what his other force is in there, similar to one of what I have in one of my rigs. So one of my systems did achieve brief spurts of anti-gravity, but the motion was too unstable. It was giving brief hops of a fraction of a second, and then getting unstable and falling back down and hopping up again, that sort of thing. A bit like the first helicopters, which also, I believe, had some hiccups in their development. So it's possible that eventually we can get these to lift off in a proper way. And more stable and compact one is in the planning phase, so we'll see if that works. And now, oh yes, I have to, because the system only allows 3 videos, I have to load on my video here. Where is it? Yes. Here we are. So I've now could you put on the one to the extreme right, Jim, the video?
My centrifugal propulsion rig. I don't want to show the details, that's why I have started working over it. This is coming uphill.
It's actually going uphill. I know this part in my living room. It's got a slight tilt upwards, only a few millimeters tilt. And that, but it's
now negotiated the hill, small hill, and it's coming on.
For example, the gyro one, 2 weeks to get up that hill.
Thank you.
Whereas this one was able to get up the hill without any problem. And sorry. Yes, that was that. And anyway, continuing, this can work for cars or aerospace. We can get a good force to power ratio of 1 Newton per watt for one, some case, or in another case, which is slightly more unstable, 20 newtons per watt. But you would need to do much development to get the more unstable one to be more stable. So the disadvantage is many moving parts that may wear down after a while. The advantage is that it actually works fairly easily. Now, hyperspace travel, again, looking at the reason for negative mass. In the Alcubierre system, you need these rings of rotating negative mass, if you recall. And if you look at a normal position vector and differentiate it, once you get the velocity, which omega r on the outside and minus sine omega t cos omega t, that then turns it into a tangential vector. So the velocity is tangential, but you differentiate it again, you get back your original position vector, but minus it. So the acceleration is actually minus towards the center, this so-called centripetal acceleration, but then you get centrifugal force outward. And the idea is that this is due to an effective negative mass, that when something is rotating, it is in some sense a negative mass. This is what gave the idea for an updated version of the Alcubierre system, that you have these, the red units here are reactionless propulsion units, and they rotate the wheels. They cause rapid spinning of those wheels up to whatever thousands of RPM might be needed to get the typically such a hyperspace effect, if that's what you want. And probably for good measure, you have a magnetic field lines being generated around the whole system. So that's my proposal for a hyperspace rig. And that would have to be in space, of course. You couldn't have that easily on the ground. You could actually have it in moving through air, but if you cause some sort of collapse of an area, you don't want it to be near the built-up area, right? So anyway, just for overall propulsion conclusions, the centrifugal force is the easiest. Now the Lorentz is too difficult, and we can go with simply with the centrifugal force for now, but later we might develop the Lorentz system. But as a joke, anything, as long as we can be in competition to Ivo with their wonderful system, which is really being tested in space with 0.05 newtons per watt, which is pretty good. In the long run, hyperspace systems may be developed. So that's it. I'm sorry I ran a bit over time, but not too bad, 8 minutes, but there you have it.
Hugh, that is amazing, sir. That is amazing. So let me take the slide down. It'll be just you and me. And you know what? I'm going to bring in Jared. I'll bring in Mitch. Everybody, so we don't have that many people in the studio. Guys, please give Mr. Hugh Deasy an enormous applause. Hugh, thank you so much. Thank you so much. That's absolutely wonderful. Absolutely wonderful. You did run over a bit. It is not a problem at all. It was such an honor to have you present. I do want to jump right into Mr. Mitch Randall, though, talking about Skywatch. If that's
yeah, sure.
Hugh, again, thank you so much. Truly an honor. And I know it was short notice and you're traveling. Let me apologize for the introduction. Also, I was loading the video for Sal Pais. It was supposed to go into the queue, and it started automatically playing, which it should.
Oh, yeah.
Okay. So thank you once again, sir, and we hope to see you back in the future with even more presentations and updates.
Okay.
Okay. Sorry about that. Mr. Mitch Randall of Skywatch. So let me do a brief intro here. Mitch will discuss a novel approach to tracking unidentified aerial phenomena using passive radar detection. It works by comparing reflected radio and other common EM signals against locally known locations. So Mitch, I'm going to launch you right into it, but I want to let the audience know you and I did an interview. You have gone on Coast to Coast AM. You have been part of the Galileo project. You have been in radar for like 40 something years. This is a real technology. This is like on my top 5 list of like technologies in general. So thank you so much. If it's okay, let me bring up, I think, your presentation, right?
That's it.
Wonderful. And I'll still be here. I'm going to mute myself and remove myself though. And thank you once again, sir.
Now, can you tell me how to move forward in the slides?
Yeah, absolutely. So if you put your mouse over the presentation, and again, this is because you uploaded it. you should be able to select the slides, and you should have forward and back buttons. And
Oh,
just
that's
let me
easy.
know. Looks like you have a video as well. Let me know when you want me to put that in.
Very well. Okay. Thanks so much for your introduction, and it's really an honor to be here.
Oh yeah, well, no, trust me, the honor is ours. It is
Huh.
again, amazing technology. So
Okay, let me dive in. I want to talk about Skywatch, which is a passive multistatic radar network for UFO tracking. It was inspired by Peter Davenport. He wrote a paper about this in the mid-90s. But the technology didn't really catch up to where this could take off the way we want it to. So that's where I came in, and I started to work with, I did my first prototype of Skywatch working with the Galileo project. Let me just kind of blast through the slides here. I just put these in here as a kind of a reference point. Just keep in mind, this is mid-90s here, a bistatic radar receiver, and that's me. This is a, again, early 1990s software-defined radio. So I was kind of at the beginning of that, and this software-defined radio that I'm holding in my hand is in this box here, making this bistatic radar doable. You know, at the time, a radar receiver was like a rack of equipment 6 foot tall. Okay, let me say, you know, if there's anything I'd like you to get out of this talk, it is that we're trying to actually get to citizen disclosure. So I don't want to just nerd out on radars or, you know, really, you know, or just some instrument that's cool or something. This is specifically for citizen disclosure. So in this talk today, I want to talk about what citizen disclosure is. And then I want to go through a top-down design for an instrument that obtains citizen disclosure. And out of it will fall these other things that we'll get into as they come up. So let's just talk about what citizen disclosure is, and you know, we can argue about it, but here's my definition, and I think it's pretty good. So it's really a mass consensus or a lack of controversy about data that proves non-human origin. And what's really important about this is if some scientific group goes off with some really cool instrument and finds some, you know, detection of something, okay, I don't call that mass consensus. I say one scientific group might be convinced. Or, you know, another example is, let's say that we all watch YouTube and we see David Grush get up and disclose reverse engineering programs or something. I don't consider that mass. It's mass, actually, but it's not consensus. There's controversy. So that means the president's not going to get up and talk about it. It means it's not going to end up in the New York Times because there's controversy. We don't know if it's true or not. So all of these little, you know, I chose these words kind of specifically to get to the point I'm trying to get at. If you get mass consensus, it means you have data that really can't be argued against, and it means everybody has that data. So it's a mass thing. So everybody can agree, yeah, that happened. And then also you want to know that data proves there's a non-human origin. So that's what citizen disclosure is. Now let's talk about how do we design an instrument to obtain that. And I just want to let you know that as Tim mentioned, as we started, actually my career is in instrument design. And there's some subtleties of instrument design that you know, you don't always think of when you look at what an instrument is supposed to do. And that'll come up as we talk about that. First of all, you know, when you think about an instrument, you might think, oh, was it a radar? Is it an optical? Is it a magnetometer? Is it, you know, what kind of instrument is it? But actually, I'm starting here. The most important thing about this instrument is the data is owned by the citizens. That is required because of our goal is actually to get the citizen disclosure. So we don't want to have the data holed away in either a scientific group or, you know, in the military or something like that. We want it in our hands. And I'm just going to throw out there, what we're looking for is non-human made structured near-Earth aerial objects. We could be looking for, you know, undersea objects. We could be looking for something in orbit. But I'm narrowing this, and for no particular reason other than there's an instrument that does this really well. So let's just say this is what we're looking for. And we know that there's been reports over the decades of crazy behaviors in the sky. And ATIP has kind of boiled that down to the 5 observables. Basically, it says that if you see an object do this, that's special. That could be an indication of non-human origin. But let's look at that, because debunking is actually surprisingly easy. And we don't want controversy. That's part of what we're trying to design for, the lack of controversy. Basically, if anything happens that you record that can be faked by a human, then it's been debunked. All we need is the possibility that something can be faked by a human. For example, a balloon has no control surfaces. A hypersonic missile goes hypersonic speeds, and maybe you don't hear a sonic boom. Maybe you don't notice, a fireball or something. So, that's something that we can do. If you see something moving fast in the sky, it doesn't mean it's extraterrestrial. We have stealth aircraft. That's one of the observables, is low observability. But we can do that. We can even make hypersonic or supersonic vehicles that have no sonic boom. Things can fall into the water. That addresses, this idea of transmedium travel. Well, we could drop something in the water that could get on a videotape, and a debunker could say, well, something just fell in the water, big deal. The one thing, though, that stands out is instantaneous acceleration. When we see something that goes, let me see what my next slide is. Will help me explain it. Now, let me just go back. When we see something that takes a right-hand turn at Mach 2, a right-angle turn at Mach 2, we know something's up, because we can't even fake that. So instantaneous acceleration really stands out. Oops. And what we really want to do, specifically, I don't want to look for UFOs, UAPs, or something undefined. I specifically want to look for objects outside the paradigm of science. We really want to narrow this down to the characteristic, or an object that has a characteristic that we just throw our hands up, we can't do. That's what's important about this instrument, and this is exactly what we're looking for. So I just want to also separate this instrument, because this is a top-down instrument design. We're not just looking for something that's unknown or something we don't understand. We're specifically looking for something that's outside the paradigm of science, something that we cannot do, and that's really important. This is, again, what that thing is instantaneous acceleration. So here's an example. If you had some kind of instrument that showed you these tracks, and we call these kinematic tracks. So, it's a record of the position of an object as a function of time. If you see this object go in a certain direction, and by the way, Tim, can anybody see my mouse? Just asking.
Let me see. Try moving it again.
Yeah. I mean, I'm kind of moving it around.
No, they can't. They cannot see it. Okay.
Is there a laser pointer equivalent in this presentation?
I don't believe so.
Okay.
I am not sure. But
all right. Well, then I'll just talk my way through it. That's fine. If you see a track like this, where an object is moving in a certain direction to the southwest, suddenly it's moving to the direction of the northwest. That the acceleration associated with that turn could be 1,000 Gs, 10,000 Gs. We don't know, but it's something that our airplanes can't do. When our airplanes, or when anything that we make goes Mach 2 and makes a turn, a 90-degree turn, it puts a radius on that turn and keeps those Gs down to something below 10, so that either the instruments inside or if there's people inside, they don't get squished. But if we see something that doesn't do that, something that can accelerate in air with that kind of acceleration, that's just something we cannot do. That's an oops. That's an object outside the paradigm of science. Okay, now let's move on with this instrument. again, I'm really trying to emphasize that this is an instrument that's designed top down to get to citizen disclosure. So I wanted to throw out this probability of detection. This is a graph from a book that Jacques Vallée wrote. And it's kind of interesting. On this lower curve, it says the sight distance. And on this, the vertical axis, we have the number of sightings. And we see this curve that goes up. So in other words, if you can see further, you'll tend to see more, there'll tend to be more sightings. This was taken out of a statistical database where people reported, what their sight distance was with each of their observations. Now it's kind of interesting. It says theoretical here. One of the curves is called theoretical. What does that mean? Is there a theoretical curve for how often we see UFOs? Well, there kind of is. It's related to the volume you can see. So therefore, if you can see 10 times further, you get the volume that you can actually see is 1,000 times greater. So that's why this curve goes so steep. It's the cube of the sight distance, essentially. So that's really important to know. And so by the way, this is a radar that I built, or let's scratch that. I worked on this radar. Many, many people built this radar, but I worked closely with this radar. It's a really high-end meteorological research radar. But if you notice, it's pretty big and just sits there. And one thing that we discovered was it's great to have these instruments that are very, very high quality and very, very sensitive. But sometimes, let's say you're searching for a tornado, what is the chance a tornado is going to come within your volume? So what we did, this is all at the National Center for Atmospheric Research. You may recognize these. This is a storm chasing truck. This is me standing in front of it. We decided that what made sense was to mount radars on trucks because we need to get that statistics up. So it's not good enough just to have a radar or some, whatever instrument it is. If the phenomenon never comes by you, then who cares? So what you need to do is drive to it, or in this case, this is called the electrodoppler radar. In the back, there is a radar sticking out the back. Again, we flew to where the weather was. So we didn't leave it up to chance. And that's a trend in instrumentation nowadays. It's not just to have a good instrument, but to have a good instrument with a high chance of seeing something. So that becomes part of our citizen disclosure. Okay, oops, go back here. I wanted to compare, when you think about, let's find an object in the sky that's doing these kinematic tracks, how do you see stuff in the sky? Normally you immediately go to camera. Therefore we're gonna have cameras. The issue with cameras though, cameras don't give you range. And we run into this all the time when people are debunking, or with any video that you see that's been posted, there's always a question, well, is this a small, did somebody hang a hubcap from a string right in front of the camera, or is this 10 miles away and this thing's a football field size? So you don't have distance with a camera, so therefore you're unable to get pretty much everything on this list. You can't get distance, therefore you can't get position, therefore you can't get velocity, therefore you can't get acceleration. So if you can't get acceleration, we've missed our main point of, as we saw before, the one characteristic we're really looking for is that instantaneous velocity, instantaneous acceleration. So video camera is pretty much the same thing. It's great to see videos, but we always see a lot of debate about them, full of controversy. The biggest issue is nobody knows how far away it is. The only way to address that with some kind of optical instrument is to have triangulation. So that would mean you'd have to have multiple cameras observing the same thing at the same time. And then you could reverse, using triangulation, you could figure out where that thing was. So now you have distance. And then using that distance, you can get instantaneous acceleration. But there's some other issues. One of them is the sight distance of a camera is really not very far, maybe 10 to 15 kilometers, let's say. If you have a wide field instrument, which is what you need in order to see the whole sky. But we go to the far right of this, and we see that radar actually hits all the marks. The only one issue about radar is it doesn't show you what the object looks like. It just looks like a blip on a screen, but it doesn't show you the structure of the object. But it does give you distance, therefore it gives you position, therefore it gives you velocity. It's impervious to weather. There's many, many advantages of radar. And in fact, there's a monopoly. The government has a monopoly on radar data. And it's probably no coincidence. We don't really get to see radar data very often, if ever. It's so valuable and it's quantitative. But people don't necessarily want to have $1 million transmitter, a 1,000,000-watt transmitter that costs $1 million, you know, at their house, or, you know, you don't want to buy that for your scientific instrument. Those and active radar, as we normally call that, is expensive. So we're going to look at passive radar. Passive radar uses transmitters of opportunity, which means, hey, there's already things out there that are sending signals into the sky. And those signals are bouncing off objects that are in the sky. And the examples are FM radio, digital TV transmitters. There's, in the case of FM radio, it can be the equivalent of hundreds of thousands of watts that are being transmitted and continuously in all directions. Mostly it's focused towards the horizons, which is fine. And there's some gain on it, so it's not exactly transmitting straight up, and that's fine. We can get around that. But it's a lot of power that we can take advantage of. And when you make a receiver for that, you don't have a big transmitter. All you now, and especially with the technology of today's the software-defined radios, the receiver can be small, light, and inexpensive. That's really important, again, for the goal of citizen disclosure. Another bonus to this is if we did have a radar that did have the location of every object in the sky, then we can use that data to get people alerted. Let's say everybody had an app, and the radar could tell people, hey, there's something coming from the southwest. Run outside and look to the southwest and get ready to record. So we can associate an app, and I call this a bonus because once you have the radar data, you have a gold mine of information. Namely, you have where an object is and where it's headed and how fast. I mean, it could take a right angle turn and not end up where you want it to be, but that's fine. Maybe you can get several people to run outside and get optical video of the object from different angles, which is a multi-sensor input. So you can use that data to triangulate and get another fix on that position of that object in addition to the radar fix. So that's a cool bonus that comes out of this. So before I go on, I just want to summarize now. That was our little blurb on instrument development. And I want to really highlight a couple critical points. We're designing instruments specifically designed for citizen disclosure. What that means is, number one, the data has to be in the hands of the citizen. Number two, it has to be deployed in a grand scale because we want to get our statistics up. We want to look everywhere so that we can get the data no matter when the thing happens or where the thing happens. And then we get this bonus of the optical data. So what we're leading towards is a network of radars. So let's talk about a single passive radar receiver, which is the heart of this system. Here's a little image that shows you kind of the setup of the whole thing. So you have, in this case, let's just stick with a FM radio transmitter. It's a kind of a beautiful signal to work with in this for this application. It's transmitting. There's a signal that comes from the transmitter and, you know, will hit your receiver. That's pretty unavoidable. And the signal also hits whatever's in the sky. Then an echo of that signal bounces off the object in the sky and hits your receiver at a little later time. There are certain cases when you are shielded from the transmitter. Let's say that you're in a valley and the transmitter signal is pretty much going over the top of the mountains and not coming down into your valley. We can do another technique where we grab a reference signal from the transmitter and get that reference signal to the receiver. And in a little bit here, I'll tell you why the reference signal is so important. It's unavoidable, as I mentioned, but it causes a big problem, which I haven't mentioned yet, but it also is essential. A single bistatic receiver has pretty incredible, one based off FM radio, has pretty incredible performance. It can see objects out to 150 kilometers. And in fact, it can go much further than that. And we'll talk about that in a minute. We can see altitudes up to 80 kilometers. Now, some of these numbers I picked here have to do with the specific setting. So you can change some of the settings and change some of these numbers, but I'm just drawing a line in the sand. Here's where we're going to set up our receivers for this application. Altitudes up to 80 kilometers, so that's pretty much near the edge of space. Velocity up to Mach 6. Acceleration up to 2,700 Gs. So we can measure that directly, not by inference, but directly. Full sky observation. And we'll get kinematic tracks at 15 samples per second. So that means I showed that picture before that showed the green lines going across a map of the country. That means that the green line is actually composed of little samples that are every 15 times per second. And the data that comes out of it is quantitative and of scientific quality. And just to kind of highlight, there's some examples here. This thing will be able to see a bird within 16 kilometers, a drone out to maybe 30 kilometers, a 1 meter sphere out to 90 kilometers, a Cessna out to 150 kilometers, and an airliner, could be out at 280 kilometers. And this is in order to obtain a 10 dB signal to noise ratio on detection. And by the way, this isn't, this isn't like a theory, maybe this will work. These things are in operation. The bistatic radar has been around for decades. As you saw, I was doing a weather bistatic receiver back in the 90s. So this stuff is proven. It's not like it might not work or something like that. It's a done deal. This technology is there. The way bistatic works is, if you can see, there's a little house in that picture, and there's a little antenna in that picture. The little house is a receiver, and the little antenna would be an FM radio station. And between those two things is the direct path distance shown with the dotted line. And then something that would be in the atmosphere that's reflecting would, the signal would come from the transmitter antenna, reflect off that, and make this triangle that you see in this picture. Now, it turns out that at one bistatic receiver, all you can measure is that delay. And that delay places that object somewhere on this ellipse, or really it's an ellipsoid in 3D space. And that's all you know right now about that object, is that it's somewhere on that ellipsoid. And also, you know a little bit about the Doppler velocity, which is perpendicular to that ellipsoid. So that's the information you know about that based on a single bistatic receiver. So keep that in mind, because a regular radar has got a much more simple geometry. It just bounces off an object, bounces straight back, and the distance is just 2R, an R going out and an R coming back. So let's look at how actually, Tim, could you play that video? There we go. This video shows the prototype system I did for the Galileo project. On the left here, and going horizontal, we have distance, and this kind of a bunch of dots that go vertically on the left there is 0 distance. And then going to the right is about 100 kilometers. And then the vertical axis is the Doppler. Now, again, you can't translate this exactly into a position, even though it kind of looks like those objects, based on what we normally look at, are, it's not a plan view of a map with objects on it. That's not what this is. But it does show you that the Doppler of each object and how far away it is. There's actually an airport that you can see in this that's right on the center line because the aircraft are coming to 0 Doppler when they get to the airport. It's about 52 kilometers away. If we can go back to the presentation. Okay. So how do you do it? We have an antenna. We use something called correlative range. How it works is you receive your signal, but you have an idea of what was transmitted, and we call that the reference signal. So you have to know what was transmitted. In the case of a FM radio transmitter, we're not demodulating it into audio like a regular radar receiver or like a regular FM radio receiver works. What we're just doing is looking at the electromagnetic energy, and it's about a certain band. You know, it's if you're looking at FM 96.3, you look at the signal that's being received at that frequency. It's basically a random phase jitter of a carrier. That's what the FM radio signal looks like if you don't demodulate it into audio. And from our perspective, it looks pretty random. A phase from one moment to the next is just all over the map. If we have a copy of what was transmitted, and then we receive an echo from an airplane, those two things at some delay, so we have to adjust some delay, then those things will match up. And we put that through a low-pass filter, and we get a detection. So I'm getting into some of the nuts and bolts here. It's kind of fun. But a way to think of that is, suppose that, suppose you take a test, a multiple choice test. It just looks like a bunch of random things when you just look at the piece of paper. But the teacher can take an answer guide and compare those and figure out, if you got the dots in the right place. But this problem that we have today with the radar is similar to having that, except you don't have any numbering on the answer sheet. And you just have a bunch of random dots that appear to be random dots. And the teacher can't line up the answer key with the test. But there is one particular alignment where all of a sudden the score goes from 20% to 90%. And that's how you can tell you're lined up. So this is pretty much how it works with the passive radar receiver. We try every delay, just like how the teacher would try to align the test in several different ways until they think it's actually lined up right. If there's an object at one of the delays we try, we will get a response because the phases coming in, that random pattern of phases coming in will match the random pattern of phases that we have delayed from the transmitter. So I hope that helps kind of bring it down to earth, kind of what's going on with that correlative range detection. And then there's some quirks to the whole thing. When we correlate for delay A, then signals of a different delay act like noise. So they don't just disappear. They're still in there, but they're just at a different delay. And it comes through as noise. This is on the right-hand side in that picture where it goes into the low-pass filter. A bunch of the signal that goes into the low-pass filter is just random noise because it's objects from other gates, other distances that are not correlating right with the reference delay that you're using for that moment. The direct signal from the transmitter to the receiver is what you use to know what that reference is, but there's a big issue with it. It's 90 dB greater than the echoes you're trying to receive. Typically, not exactly, but typically. And that's a 1 with 9 zeros behind it in terms of power. So that's a big number. And you do have to go through some maturations to get rid of that in order to get anything to happen in your receiver. And that direct signal, isn't lined up with the delays of the other gates. So that looks like a noise. And that noise raises the noise floor by tens of dB. So if you don't do something to get rid of that direct signal, you'll have no sensitivity in your system. What you need is an adaptive noise canceller. And how you do that is you take two antennas, you point one of them in the direction of the stuff you want to see, let's say point it towards an airport or towards some region of interest, and you point the other antenna at the actual FM transmitter. That really helps a little bit, at least. It gets rid of it gets rid of some of that 90 dB. It chops it down to maybe 70 dB, but you still have a 70 dB problem. To address the rest of that problem, you use an adaptive filter echo canceller. So this is just a picture of one. I'm not going to get into the details, and you can look it up. And there's also papers on bistatic radar go through exactly how to do all this stuff. None of this is, like I said, none of this is unknown. It's all been done before. We're just repurposing it for this very specific application. And so the other thing is, if we want to have this as a network that, let's say many of these are fielded, we can't be having people steering antennas around, pointing them at the radio transmitter and pointing them at the area of interest. This all has to be done automatically. So we use an antenna array to do that, and we use adaptive null steering and beamforming to essentially digitally create 2 channels that we can do this processing with. And here's an example of a 3-element array. This is for the Galileo project. 6 of these were built and fielded in Massachusetts for the Galileo project. The processor is in this little box here, and you can see the 3 antennas. But the idea is it would do 360-degree null steering and 360-degree beamforming, so that you can get at least that first 20 dB of kind of, chopping 20 dB off of that 90 dB unwanted signal. And that null steering looks like this. So what you want to do is point. So this is a circular, a polar display of the power received from any direction, or the sensitivity of power looking at any direction. And so you want to take this null and point it towards where the transmitter is, but you can see that the reception at everywhere else is pretty decent. Maybe, just a little bit of loss at all the other places, but right towards the transmitter, maybe a 30 dB dip. So that's one way. That's the first step in getting rid of that unwanted signal. Oh yeah, and here you already saw that other picture, but I just kind of repeated here. And here it has the label, so that's kind of helpful. You can see there's 0 hertz in the center. So this is, again, that display that shows you Doppler versus range. It goes from 125 hertz to minus 125 hertz and out to 120 kilometers in this case. Okay, so to get the statistics up, we want to make this in a nationwide network. And also, it's not good enough to have that display that I just showed you that says, bistatic range versus Doppler, because you really need to know position. You need to get the location of an object. Because our goal, just to kind of bring us back to ground here, the goal is to get those kinematic tracks, and the goal is for everybody to get those kinematic tracks, and multiple instruments watching that, and everybody observing that and owning that data and believing that data, so that we can get a citizen disclosure. So let's just go through how that works. If, like I said before, if you have one receiver, you don't know where on that ellipsoid that object is. But if you have 2 receivers, then you can figure out at least a line in space that it's going to be in. If you have 3 receivers, it narrows down to 2 points on that line, and 4 receivers gives you 1 point. Let me just give you an example of what I'm talking about rather than just the words. So let's say a receiver on the left there. So there's one transmitter in this example, a receiver on the left and a receiver on the right. And they're seeing some object. And on the left, you say it's anywhere on that ellipse, and on the bigger ellipse on the left. And on the right, you say that receiver sees something somewhere on this squished ellipse on the right. But what we know, if that's the same object, they can only be, that object must be somewhere on that line where those 2 ellipses intersect. And they're ellipsoids, again, they're eggs, and they would intersect in a curve, probably an ellipse, in that other dimension that's drawn as a line here. So just from 2 receivers, you can narrow down the position of an object down to that circle, or that ellipsoidal line in 3D space. So what we want to do is make sure we have a grid where no matter where an object is, it's going to get picked up by at least 5 5 is my minimum number. Even though 4 works, 5 is overdetermined. But you can see when you do that, you get 3D position, therefore you get 3D velocity, therefore you suddenly get the ability to measure instantaneous acceleration by watching how the velocity changes with time. And then if you get more and more detections, you just have more and more certainty that what you're looking at is valid, and you can get a finer resolution to it also. And in this case, you can see that if the radar if these spacings are 30 kilometers, which is a typical kind of spacing for this system, many of these receivers would be able to, probably every dot in this picture would be able to see the red dot in the middle that I've drawn there. So you would have a very overdetermined and very accurate and very indisputable detection if you got all those detections from all those systems. And the cool thing about FM coverage is it's everywhere. I mean, there are some gaps in here, but this is a map of the 60 dBmV radius of each FM transmitter in the United States. But actually the radar is quite a bit more sensitive and can go further than that 60 dBmV line that you see there, or the curve for each one of those. So the nation is pretty well covered by FM radio transmitters, which is very cool. That means we can have a volume that is so huge that we're so far up on that curve that I showed you earlier that the chances of seeing an object become very, very high. In fact, if there's any object over the United States, we're going to see it. To cover the entire nation is, like as I mentioned, a 30-kilometer grid. That's about 10,000 radar receivers. That means that if you wanted to just have 5 receivers pick up something, none of them would have to see more than 44 kilometers. Those are all really good conservative numbers. If you got those detections within that range, you'd have high signal to noise ratio, very good accuracy on the measurements, and likely to be really overdetermined by the additional receivers. And here's what it would look like on the map, just to give you an idea. That's Minneapolis, just as an example, where the receivers would be in order to get this perfectly square grid. In reality, what we want to do is put a product on the market so that people can buy this and put it on their house. And we don't know where their houses are going to be. And maybe in a city, there'd be 30 in a city, and then a few out in the country. So we don't, the spacing isn't going to look like this perfect grid here. But if we can at least get this as a minimum, so at least make sure that no point is any further away than this grid would allow, then we've achieved a pretty good goal. But some people have mentioned, I think Tim and I even talked about it on our interview, you don't have to have 10,000 systems out in the world for this to work. You could have 5, because 5 has a pretty good, pretty good coverage range. And you can get data out of that. If you're lucky, you might see a right angle turn. Okay, now another thing that's really important about the system, I have to just make sure I'm doing good on time. Another thing about this system is we do real-time calibration. It's very convenient to use aircraft ADS-B data. And if you're not familiar with that, every airplane, commercial aircraft and private, almost, let's just say a lot of the private aircraft as well, are equipped with an ADS-B transponder. These transponders ping their location and their velocity based on a GPS measurement. So you can put a little receiver along with the system. There can be a little ADS-B receiver that picks up all the aircraft in a pretty good radius and knows their exact position. So if we know the exact position of airplanes, the radar picks them up, as I showed before, quite easily. And the position of those airplanes, we can use that, the system will figure out where the position of those aircraft is and can compare that to the ADS-B data. So that is a really convenient and clever way, or cute way, of keeping the system in calibration or detecting any receiver that might have any kind of problem. And it's kind of interesting because this would be going on 24/7. There's pretty much always airplanes in the sky every moment of the day, especially in this 150-kilometer radius. That's enough to see 100 airplanes at once almost every moment of the day. And those will all be being used as calibration in the background to make sure it's really calibration and validation, right? To make sure the system's working and none of the receivers are doing anything they shouldn't be doing. And if at the same time an object comes through that volume and makes a right angle turn while you're simultaneously detecting the position of all those aircraft and proving that those are correct, there's going to be very little doubt that that object that did that right angle turn, that measurement is also correct. So this validation turns this from a hobby thing that you can put in your house or whatever, it turns it into a traceable, calibrated system that can be used to reliably obtain, quantitative data. And that's a pretty awesome thing. And that's part of, again, we designed this system specifically from the top down to be uncontroversial in the data that it provides. When it shows something doing some, a crazy maneuver in the sky, there's not going to be a question whether that was an anomaly. That it's going to be pretty much a done deal. And, as part of this, there'll be a web display that's similar to what we've seen for these, there's flight tracking websites out there that show you a plan view of the United States. You can zoom in where you want, and it will show you, the aircraft that are flying around. The idea for Skywatch is the same thing would be available, except now it shows you, actually we would declutter the screen with all the known aircraft, so you only see the anomalous aircraft, but everybody would have availability to that. So if there is something that flies through the sky and does a crazy maneuver, everybody that's watching can see it, and there's no barrier between you and that data. The citizens own this data, and that's critical. Okay, and then this all boils down to the way to make this instrument work is to have this network, and the way to have a network is to have low-cost consumer receivers. So to get to the point where citizens can put this on their roof, there'll be a box that goes in their house and an antenna on their roof and a little cable between the two. That's as complicated as it gets. It'll be plug and play and very easy to manage in terms of, like, if somebody can install a printer, they can install the Skywatch receiver. And then the calibration that's built in will make sure that it's been installed correctly, because we'll be able to see if it's working correctly. What needs to be done to make this consumer Skywatch receiver is to develop a low-cost consumer receiver and develop now the hands-off antenna. That means an antenna that can electronically steer that null and the main beam, and develop the server backend that's going to be the interface, the user interface for people. Go through the development of the real-time calibration. And if you're an engineer or product developer, you might notice that nothing on this list is like make some magic occur or something like that. Nothing is everything here is just turning the crank on stuff that we already know how to do, but it has to be productized, and it really has to be productized to the degree that there's support, there's manufacturing, there's distribution, there's even marketing. All that stuff has to be in place just like any other consumer electronic product. And that's it's a handful of work, but there's nothing that's, we don't know how to do. I want to mention here, as part of this, there's going to be a few papers published in peer-reviewed journals that describe the system, just pretty much summarize or expand on the things that we just talked about today here, to describe the system, and also a paper that goes through in detail the error bars and when you do get an answer, how accurate or what are the limitations or what are the ins and outs of that? Because of course, as any instrument, there are definitely limitations, and those need to be spelled out in a peer-reviewed journal so that scientists know how to use this data. And that's important, by the way, because this data is critically useful to scientists. It detects, since the system, Skywatch system, detects exactly where an object is, now it becomes much more relevant for a scientific organization now to train their telescope on that thing, or train any, move their broadband antennas and point at that thing. So there's a bunch of narrow field instruments that can be vectored to the direction of the object, but you need to know where the object is before you can do that. And also, if there's some kind of hotspots in the United States or whatever that this thing detects, that will be a huge, important clue for groups with scientific instrumentation to go there and set up their instruments that might be less portable and don't have as much volumetric coverage as Skywatch. And by the way, nothing will have as much volumetric coverage as Skywatch because it's designed to cover the entire nation, which is part of the whole thing. So here's that box I was telling you. This is just an artist's conception. We don't have it designed yet. It seems like this is a very doable kind of configuration. It's not going to be so big. The antenna also is an artist's conception. It's not going to look like that exactly, but the idea is it's small and possible for someone to install on their roof, within the guidelines of HOAs and whatever. The status of it is right now, a proof of concept has been completed. So we saw those, the video I showed you, we saw airplanes flying in the sky. It has no trouble detecting those. We deployed the network in Galileo. We took a bunch of data. There's a lot of data we can process to do some of the combinations and the actual position resolution with it. We wrote a peer-reviewed paper. I'm the lead author on that paper. It was in the Journal of Astronomical Instrumentation. And where we stand right now is we have scoped out the entire consumer product development. We know how long it's going to take. We know what the amount it's going to take, the funds it'll take, and we're fundraising for that right now. So, you can't buy one right now. That's not where we are. But we know how to make one, and we're looking for philanthropic funding to come through, because this is a philanthropic project. This isn't a big profit thing. It's going to make everybody $1 million. This is the cheapest possible receivers we can put on the market to get the broadest possible adoption of this, for a pretty narrow field. So I think we can get 10,000 products out there, but not if they cost $10,000. We got to keep the price down, and we got to make it really easy for people to use. And you don't need to have a degree in order to use it. It's just plug and play. So in summary, this is my last slide. The Skywatch passive radar UFO detector is designed to enable citizen disclosure. It is purpose designed to do that. And if you take anything out of this talk, that's what I want you to really get, is that if the object is citizen disclosure, which to me is, I wouldn't accept anything less, because who cares if we get some interesting, blip on just some other instrument. If you don't know where the object is and it doesn't resolve to a determination that that's an interesting object and it can be debunked, then I don't really care. But this instrument, Skywatch, that I just showed you, is specifically designed for citizen disclosure, because when we see those kinematic tracks with those right angle turns, or stopping and then going backwards or whatever, we have found something irrefutable. So that's my talk. Thank you very much.
Let me bring myself back in here. Mitch, thank you so much. I'm going to have them clap, but before that, what I want to do very quickly is, let me see. I want to share my Skywatch tab there, and that way people can see your website. I put the link in there. It's not showing the link. It's Ascendant, ASCENDANTAI, ascendantai.com/Skywatch. And they can learn more about the project there. And I will scroll up briefly for them. Inspired by Peter Davenport. Again, I am so excited about this. And so I just want to convey that to the audience. This is the real deal, right? Because a lot of the technologies that we work with are very theoretical, or they're in the rudimentary stages of testing, or we're testing ideas or whatever. What you have is, it is basically fully developed, right? And so that doesn't mean that it's out there in the market that people can buy yet, but what it means is that you can build it, and it will be put together, and it will work, and it will help detect and track UAP, which is something that is desperately needed, absolutely desperately needed. So again, Ascendant AI.
If you scroll down a
Skywatch.
little bit, you'll see our interview.
Ah, okay.
There you go.
There we go. Okay.
Don't miss that.
And you know, I can drop I'll drop a link in there as well. Again, I love detectors, and one of the reasons that I love detection systems in general is because the bar is lower for success, right? You don't have to propel anything through space, you don't have to warp space and time. All you have to do is detect and track the signatures for something that is. But then the other part is this could give us so much valuable data, you know. And there are I mean, like SETI at home was one example of this, where you basically you're kind of crowdsourcing, right? You have this open source network of people that are contributing to something larger, and Skywatch is perfect. You know, I absolutely love this idea. So let me thank you for presenting, but I also want to here, I'm going to I will remove that. Okay. And I'm going to bring the guys in here. I think that's everybody that we have. Okay. Andrew's not there. Guys, let's give an enormous hand for Mitch Randall. Mitch, thank you so much. I don't know if it's coming through, but I'm like your #1 fan, and you have tons and tons of fans out there as well. So,
well, thank you so much. It's a terrific opportunity to be able to present this and let the world know that this thing's ready to go. Yep.
Yeah, absolutely.
Can I ask one question?
Yeah. We don't have a lot of time, but go for it, Jared.
Mitch, awesome talk. There was one burning question in my mind for the whole presentation, and that's the engineerable data that we could get out of it. Is there any way that we'd be able to detect polarization changes, especially during maneuvers, especially triangulated, so you could see, oh, look, when we look at it this way, the polarization changes one way. When we look at it the other way, the polarization changes a different way. Now we can start integrating that information into our engineering ideas.
There's that, and there's several other things that I would say are kind of a next generation. The first generation doesn't have that. We're sticking with one polarization, vertical polarization in particular, which, by the way, in a bistatic radar, vertical is kind of the deal, because if you have a horizontal polarization and your reflection angle is 90 degrees, you might see nothing. So there's an issue there with the geometry of scatterers and polarization. But there's what you just mentioned, plus several other things we want to add to a second generation. But, you know, I'm focused right now on getting this out. This is important enough, I think, on its own. Great question, by the way.
Wonderful. Well, guys, let me wrap this one up because we actually have a big presentation coming up. But again, Mitch, thank you so much. It is truly an honor, sir.
You're welcome. Thank you.
Okay, so next up, and I'm going to hope that this starts to play without a hitch. I have not done a video like this before. Dr. Salvatore Pais and Dr. John Brandenburg had a discussion about Pais Superforce. For anyone who follows my interview channel, I did an interview with Dr. Pais a few weeks back, and that had a lot of interest. He has also been publishing a paper on the Superforce, and I will try and track down a link to that and put that in chat. I'm not going to get into the details of it. This is something that Dr. Brandenburg talked about on a past APEC. He got very excited, and that's actually what prompted this discussion. So we sat down. This was just about a week ago now, and we recorded. It was actually the full discussion was 2.5 hours. A lot of it was just them catching up, comparing notes, talking about, you know, old times and friends and things like that. And we also brought in Mark Sokol. We brought in a lot of the APEC team at about an hour. And so the first half of this discussion is John and Sal just talking about the Superforce and some of the notables. If you want the details, again, I'll put a link up to the paper and my interview and all of that. This is more of kind of a commentary on it, where they compared notes and went over some of the big ideas. The second half of this is a discussion with Todd Desiato and Sal, And they ended up discussing this at length for about half an hour, and they had really wonderful insights. So I went through and spent actually a long time editing this. And when I was going through, I was like, okay, what is important? What is relevant? And we have just about 55 minutes of footage here. If you guys like this, we can, and we probably will record more in the future because, again, Dr. Pais' work it's gotten tons of media. It has influenced many people. I think a lot of folks consider it kind of mysterious in some ways, right? It's not as well understood as some others. And so this is something that we want to try and get out there and just help educate and engage as much as we can. So let me see if I can play this for you. And if this works, I will once again disappear into the background for about an hour until Dr. Sarfatti comes on, hopefully. For John Brandenburg here, and they will be discussing the Superforce. So without any further ado, I am going to once again hide my self view, spotlight you gentlemen, and you guys can get into it.
Very good.
Thank you for making this possible.
Yes, thank you for making this. I'm so pleased to be part of this meeting. First, and may I call you Salvador? Or what would you like to be called?
Sal is fine. You can call
Okay.
me Sal.
Oh, Sal.
It's fine.
Sal.
Yeah.
Sal.
Sal.
John.
Sal.
Okay.
Sal
Sal,
Banana. Okay.
your Superforce thing is brilliant. And
no,
it's
sir.
part of it.
Your
No,
STEM
part of its
theory, sir.
brilliance is that it is so simple, yet it is a small step mentally, but an enormous step conceptually.
Thank you, sir.
Like to paraphrase Neil Armstrong on the moon.
Coming from the originator of gem theory that actually gave us the mass of the Higgs excitation before it was found experimentally, by the way, at the cost of billions of dollars.
I know.
You only gave us so close to 125 GeV, 125 times the mass of the proton. You were the first to put it out there. So I ask you, sir, where's your invitation to Stockholm, and where's the little pin on your lapel? I believe it's gold.
Hey, I'm more interested in the $1 million check at this point. No, I believe my work is slowly being recognized. Paz, we're a part of a revolution, and we are breaking out of the regime of the string theorists. You know, the thing I love about your Superforce is that it is simply an inverse force. They had convinced me because of string theory that it was a energy per unit length of a string. And then you said, oh no, that's energy over distance. That's a force.
Yes, sir.
Where did I walk into?
Okay,
Yes,
let's go back to the Superforce equation. So equation
The
one.
Superforce equation. Very important.
If you look at it, it really says the Superforce, the c to the fourth power divided by big G.
Yes.
Is equal to the energy gradient at both the Planck scale and the horizon scales. And that's what makes, well, actually it's on the order of magnitude of both the Planck scales and the horizon scales. In other words, it goes from the realm of the very small Planckian, you know, the realm of strings.
Yes.
To the realm of the observable universe. And this is what I believe this equation is so important. Now, Dave Chester said that this particular equation, he thinks he's been able to derive it from the Dirac large number hypothesis. And I'm like,
very good, very good.
And he was trying as a result to sort of say that it's being marginalized because mainstream physics right now does not recognize the importance of Dirac's large number hypothesis. However,
it's just a coincidence, they say. Just a coincidence.
Yes. But this is key. If I'm right and this formula holds, then this exonerates Dirac. This means that the Dirac large number hypothesis is no longer coincidence, but it's fact. And
it is.
What is truly, and what is truly, I think, very important from my point of view. The way I look at it, okay, he also asked me why the energy gradient. And I said, wait a second, how would you describe an acting force in a system that you do not know the dynamic state of? It has to be an energy gradient. Hence, a characteristic energy divided by characteristic length. Again, we follow, just like you and I, both you and I follow Occam's razor.
Occam's razor.
And minimalism. Simplicity and minimalism. You can't get anything more simple or minimalistic than energy gradient describing an acting force.
Simple dimensional analysis leads you
right?
to the...
Remember,
but yes, getting back to your Superforce.
Yes, sir.
Now you believe you have connected this, and I am not a quantum field theorist, even though I it is a useful limit for me to dabble in, down to the Planck scale.
Yes.
That's a very good boundary condition that I use. But yes, I am not, by training or even outlook, a quantum field theorist. So you'll have to forgive me. And I'm trying to learn, by the way. I'm trying to learn. So if you could walk me through your Schrodinger.
Yes, yes, absolutely. If you can permit me to put on my reading glasses, I'm getting to a certain stage where I no longer have what, how should I say, the sight that I once had. Oh my goodness. Well, I used to be able, I still remember being able to read. I was absolutely, I used to read things that were at least maybe 100 feet away. I used to be able to read something that was on the size of about 2 inches. That's not bad, 100 feet.
That's not bad.
Those were the days. Now I can't hardly read this. That's how bad it is. Anyway, so Sir Penrose, which I believe Lord Penrose, so
Lord Penrose,
King Charles III, Your Majesty, if you ever watch this, please make the man a lord.
Make him a lord. Elevate him to the peerage.
Yes, he deserves it, among all others. Now, so Penrose writes, as a simple example, using the particular case of a quantum Hamiltonian, we can now write the Schrodinger equation for a single particle of mass m, moving in an external field whose energy contribution is V equal V of x, y, z, of course. But again, the particle of mass m is moving in an external field whose energy contribution is V equal V sub x. And this is a very important, because David Chester challenged me on this. And here's the response to his challenge. I thought it through. And if you can listen to this, please do. So if you remember the Schrodinger equation, it basically, it has an imaginary part equaling to what you'd call a momentum part, plus its rest energy of the background field. Let me take this off. It makes me look like my, anyway. So this V sub x, now Dave Chester said that I am actually introducing the Planck scale in such a way as to give me the superforce. So in other words, I'm putting the superforce in to get out the superforce. That's what Dave Chester.
Who said this to
you? And I remember you stating something of that same nature in your APS conference. I remember. I think you may have been on APEC. But anyway, we'll discuss this further. Let's focus on the Schrodinger equation.
Yes.
Maybe this is a sort of, anyway, so Schrodinger equation.
Continue.
And the whole idea, again, simple mathematics.
Simple mathematics.
There is something called conditional replacement technique that I came up with in a paper that I call him Dr. Paul Murad, so I'm not gonna stop. So Dr. Murad read that paper. It took me 4 years to publish it. It's called conditional possibility of spacecraft propulsion under superluminal speeds, or rather at superluminal speeds. And in it, I describe a technique, a one-to-one correspondence technique called conditional replacement technique. I'm not using that in this paper. What I'm using in this paper is something I call, again, I think, okay, think of the terms in an equation. They are there because they're important. So every one of those terms has relevance to that equation.
Yes.
So as far as the physics is concerned, think of physics. Don't think of mathematics now. Think of physics.
Physics.
From a physical, right. From a physical mathematics perspective, whereby physics drives the mathematics, it actually says, when you have an equation, say A equal B plus C, it says that from a physics perspective, from an order of importance, A is of the same order of importance as B, is of the same order of importance as C. Otherwise, they would not be there.
No.
There would not be terms of this equation. So from a physical perspective, they are of equal importance. So what I did, if you look at, do you remember the imaginary term? It's on the order of I, H bar, d psi dt, the partial of the wave function. It's a time derivative of the wave function.
Yes.
Okay. Now, you remember what V sub x is, what Lord Penrose says V sub x should be. It is basically the rest energy of a field for which the particle of mass m is moving. So if you take, okay, so since all terms are of equal importance, you take that imaginary term, the I H bar d psi dt, okay? And you take that last term, the V sub x, and you equal them. Equal importance. Just simple, very rudimentary, but again, looking toward physics. Look carefully what it says. Forget about the imaginary part, because remember, remember Euler's formula, the whole idea of e to the I prime plus 1.
Yes, it is a rotation.
Yes, exactly.
It's a twist.
That the imaginary part, the e to the I theta equal cosine theta plus I sine theta, everything is equally important. Just because it has the I in it doesn't mean you disregard the sinusoidal function. Agreed? See?
Absolutely.
Again, physics driving the mathematics. This is the beauty of it. Okay, so from that first term, that I H bar d psi dt, and the same order as Vx, if you look at that, V sub x is really an energy. It's the background energy, the rest energy of the field for which the particle of mass m is traveling. Now, according to Penrose, Lord Penrose.
Yes.
Okay, King Charles, please. Okay, okay, so if you look closely at that H, right? H divided by dt, it's really what? What's 1 divided by t like? A frequency. H bar.
Yes.
See? Do you want? It's the Planck-Einstein equation for what?
Oh, so you can get the Planck, length from the Schrodinger equation.
Yes, sir. Thank you.
I've never seen that done.
Thank you. This is how easy this thing is. No, eventually I'll show. There's a little more mathematics involved where you can show the when you equate terms, I believe 1 and 2. So you equate the one that has the mass of the particle in it, with the first term, with the I H bar d psi dt. When you equate that, you get the de Broglie wavelength. When you put it out, trust me.
Okay, I will.
When you put the reference length as the lambda of that moving particle, again, particle wave duality. That's the whole idea.
Particle wave.
You get the de Broglie wavelength on the order of h bar divided by mv, which is the momentum of your particle. Right?
Right.
The Broglie's equation. Okay, and now this is the pièce de résistance, is the French say. The pièce de résistance is this. When you take term 2 with term 3, and this is unbelievable. When you take term 2 with term 3 and do a little manipulation, and you put for your characteristic length.
The term 3 is the potential.
Yes, remember, it's the rest energy of the background field for which the particle of mass m is moving. So when you take term 2, which is the one that has the particle mass in it, and this v sub x, and you put for your characteristic length gh bar divided by c cubed, square it off, right? Because
blank length.
That's blank length. You get what? You get for your energy gradient. When you do the energy gradient,
the Superforce.
You get c to the 4th divided by big G. So David Chester cannot say that I put in the Superforce and got out the Superforce. What I put in is exactly what I said. The Superforce resides at the Planck scale. At the Planck scale is what? Planck length. So therefore, your characteristic length must be G.
And that means you have a potential. And if you divide it by the Planck length, then you get the Superforce.
How? Why is the Superforce in the Schrodinger equation? And it's an easy manipulation to show if it's in the Schrodinger equation, as you well know, because it's a linear system, it's a linear equation. The same thing applies to the Dirac, because Dirac is just Schrodinger plus special relative.
Yes, it is.
Thank you.
Hey, Sal,
anyway,
about the Superforce, or I always called that the Planck force.
Yes, it is the Planck force.
It is. And all these Planck scale objects, Planck length, Planck time, Planck force, Planck charge, even like the fine structure constant, I look at it's E squared over the Planck charge squared.
Right.
It's same, it's all in there. I just see these as a baseline based on our own man-made constants that we created to equate to the units we defined. And it's like, to me, it's like you have a deep bucket with a flat bottom base, and up here on the top, the wind's making the top ripple, and that's what we have to work with. And down here at the bottom of the deep bucket, you got a baseline that you can't change.
Yep.
Agreed. Good observation. Now
none of that really has any, let me finish. None of that really has any effect on anything we can do other than reference it as a common baseline. I did a paper about this back in like 2004, where I took Hal Puthoff's PV model, which is an analog of curved space-time.
Yes.
And I looked at it from what would it look like on a flat tangent plane. So what would it look like if you took the PV model and wrote it and revised the mathematics to describe the same thing without a variable speed of light? And what you get is a variable density function instead of a variable impedance function, instead of a variable refractive index, instead of it changing the speed of light, 1 over mu naught E naught square root, it affects mu naught over E naught, the impedance function. But there is a complete, mapping, one-to-one mapping of all the equations over from one to the other. And that mapping depends on dividing by different multiples of Planck scale objects. So you would map length from the curved space-time model to the flat space-time model by dividing length squared by the Planck length squared. And then using the density function, the impedance function, would map what that would be in terms of a refractive index in a polarizable vacuum model. And so it really is nothing more than a baseline for mapping one frame of reference to another. And
I disagree. And let me say why. Let me disagree with you. All right. Todd, we find this Planck force in the general relativity equations of Albert Einstein.
Yeah,
which
it's
they
force
shouldn't
relative to the
be
Planck
there.
force.
The Planck force, which is a Planckian quantum, actually, if you think of it, it's the only Planckian variable, or rather the only Planckian parameter that does not have h bar in it, does not have the quantum of action in it.
It does. It
Which
just
means-
canceled out twice.
Which means that it can it can operate on the classical realm as well as the quantum realm. Why?
It's true.
Because it talks to super density. Remember, a super density, if you think of the Planck force, think of it like the force is on the order of a pressure times an area. So what we're talking about is like the super density times c squared times L squared P, where LP is the Planck force. That super density comes out to be on the order of c to the fifth divided by g squared h bar.
Mhm.
So it's on the order of 10 to the 96 kilograms per meter cube. 10 to the 96 kilogram per meter cube. Well, I'm arguing there's an analogy between our mechanism of supernovas based on core bounds and how the superforce gives rise to a superbang at the super density.
Okay.
This
That
may
makes
be a
sense.
whole different perspective on inflation. It may actually give us, okay, my question is to the illustrious mainstream physicists. I ask, what is a Planckian parameter doing in general relativity? Because you can actually
Can I answer that?
No, let me finish and then you can answer any, I promise. But this I must say, because it gives a certain conclusion. It reaches a certain conclusion, in my opinion, a new perspective on all physics. Now, it's not new physics. It's a new perspective on all physics. And this is it. If you look at Einstein's G sub mu nu on the order of 1 divided by Planck force or superforce times T sub mu nu, it actually says space-time curvatures on the order of 1 divided by the superforce times the whole thing times T sub mu nu. Now, these are same rank tensors. They have to be. Otherwise, right? That's a scalar parameter. Put it on the other side. What does it say? It says the superforce acting as a linear operator on the local spatial-temporal geometric structure gives rise to energy density, hence matter. Do you remember a certain, and this is what I question.
You're saying.
No, listen, just one more thing, and I promise you can talk for the rest of the thing, but this is important because I'm putting it out. Tim might want to cut this out because maybe mainstream physicists listening to this will say, my God, this is total crackpot. But what if 3D printing out of space-time fabric is feasible based on the action of the superforce? If we can nudge the superforce, we can actually, maybe this is how quote unquote ET tech works. And this is what I'm really weirded out by. The way Bob Lazar describes the sports model, saying it's as if it was grown out of space-time itself. Well, this freaking equation talks to that. What if this guy's not full of shit?
Well, doesn't that goes to entanglement and quantum teleportation and things like that?
Oh, that
also,
too,
right?
of course. But it also goes to something he said, which is very strange. Anyway, yeah.
Well, to get to back to your question, and that comes out because I mean, and John would probably verify this too in GEM, that if you look at what is the gravitational impedance equation, you're going to get G over C squared. And in terms of Einstein's equation, when you want to convert from energy density and go to curvature, which is what everything has to be in to do geometry, the unit of conversion from one to the other is 1 over the force. And just like I was saying, the most natural baseline to use which really has nothing to do with quantum mechanics. It has to do with how we classically defined our units of measure, would be to reference energy density to the Planck force. So energy density over the force gives you square meters, which is curvature. And that's just the natural way things would go. It's classical. It's not quantum. It's classical. But even classically, our human defined units of measure, the way we defined a meter from the king's thumb to his nose, is referenced in all of those constants, because it's referenced in energy, and Planck's constant converts from energy to frequency, and force, and Newton's constant converts from energy to force, and they're defined on units of measure that we created as human beings. And John likes to work in CGS, and I like to work in SI. His CGS numbers drive me nuts.
I worked in SI.
I have to convert everything when I read his paper. But this is just.
I don't like dragging the factor of pi or 4 pi.
I agree, but it was drummed into me so long, talking with so many other people.
I know.
If I don't do it that way, it just confuses everybody else.
I can testify that is true.
Yeah, but anyway, so what I want to say, Sal, is that I don't believe in space-time. I think that's a misinterpretation. General relativity does not, Einstein's equation does not say what people think it says. What it says is that given the right-hand side, T mu nu, this is everything we know about matter and energy and quantum mechanics and the strong force and the weak force and all the other forces all fall under T mu nu. And given instruments made of matter, clocks and rulers made of matter, under the conditions set forth by T mu nu for the volume of space-time we're talking about and the matter in it, it describes what we will measure on the left-hand side using rulers and clocks made of stuff from the right-hand side. And space-time is no more or less than what we measure with rulers and clocks and instruments made of matter and energy. It's not a fabric. It's not a thing. These are the things. T mu nu. These are the things. Everything else on the left-hand side is the stage. And we measure what we want. What we measure is due to the quantum interactions between the things, not the stage.
Interesting.
So a ruler contracts in a gravitational field because the probabilities, the probability amplitudes for all that matter interfere with each other and cause damping. And when you add just a tiny amount of damping to a quantum harmonic oscillator, its wavelength contracts and its frequency slows down. So all you have to do is consider in our normal quantum mechanics that if you simply consider the damping that takes place because of non-coherent interference or incoherent interference between matter, and what that does to the atoms, which are just spherical harmonics, they're going to contract, they're going to slow down, and it explains gravity without ever invoking the need for a space-time manifold. The manifold is something that we measure using matter and energy.
I like where you're going. I was gonna add some
This is
humor,
why it's so hard. This is why it's so hard to make general relativity with quantum mechanics, because general relativity is not needed. It's an interpretation. It's a misinterpretation.
Can I say something?
Please. And Jeremiah.
Okay, let me say this, and then Jeremiah can take the next thing. I believe, it is my strong belief that Einstein's general relativity is not only correct, but is actually extremely close to the final solution. I think he was extremely close to it. The reason that he, anyway, I'm not going to go into the reason why he could not come up with a unified field theory. Only a great like Einstein would go there. So I am just a mere apprentice of the man. What I'm trying to say is that the superforce equation would not hold correct if there was not a link between the realm of the very small and the realm of the very large, the observable universe. The superforce equaling the energy gradient at both the Planck scale and the observable universe scale known as the horizon scale, that cannot be a coincidence.
No, it's not.
And that comes right out of GR. So if GR is wrong, everything else is wrong, including what? The freaking Dirac equation, Schrodinger's equation that has been proved over. And why? Because we find, I looked over the first segment of this where I explained to Dr. Brandenburg exactly how I find the superforce in the Schrodinger equation. How can the Schrodinger equation show the superforce is there if the superforce was not important? And the superforce also is important. You cannot tell me that Einstein knew that was the Planck force. I do not. Einstein refused to believe in quantum mechanics. As a matter of fact, he was very much against it. The Bohr-Einstein debates are some of the most fascinating dialogues in the history of science. It's absolute amazement. I mean, the idea of quantum entanglement, wow. And I tell you, Bohr almost lost the one based on Einstein-Rosen bridge, the idea of ER equally. Anyway, Bohr almost lost that one. And then he remembered that Einstein wrote this little something. He actually used Einstein's own writings against him. That's how Einstein lost the final debate. Can you imagine having your own work used against you? Todd, I would have freaking died. I would have been so pissed. I would have knocked Bohr through the wall. I don't care. You know what the.
I was on Usenet in the 1990s. I got a skin as thick as a turtle.
Very good.
That's right.
That's good. It's good to have that skin.
No, but between you and I, hey, Doc, would you agree with me? When people get physical, you know they love the physics.
Yep.
That's true.
That's for sure. Hey, well, so that relationship you mentioned, did you know that if you take Friedman Walker Robinson equation and the reciprocal interpretation of that equation, and you take the Hubble constant, Hubble constant equates to, say I had a meter stick in my hand. Okay, the Hubble constant equates to this meter stick contracting 6.8 nanometers every century.
Oh, wow.
So if the size of this meter stick depended on the quantum environment here, causing it to have this proper length, and here energy is running down and decreasing such that my meter stick is contracting 6.8 nanometers every century, and I look back in time as I look out into space, and if everything were doing this from a common Big Bang or a common starting point, then what I would see is everything will appear to be accelerating away from me and redshifting because my ruler is getting shorter relative to those wavelengths. And so that would connect the cosmic horizon to the smallest scale here on Earth.
Jeremiah needs to speak.
Yes, please.
Jeremiah, go ahead, sir.
Okay, so in one model here, Todd, you're presenting us with a stress energy momentum density equivalent in space-time that allows us to calculate out the, well, curvature equivalence, or in the more correct terms, the actual energy momentum in any given volume of space and its gradient, if one should apply, particularly in mass. The issue with it is, well, the mechanism of action there for curvature does not actually reveal the underlying substrate that causes the curvature to take place in the first place. So
Yeah, it does.
we,
I said
so
it
we,
once. Go ahead.
well, it's field force interaction based on measurements, but they don't actually reveal the underlying substrate of why there is said distance over X space and time. Hence,
Probabilities.
well, it's beyond the probability scale. We have to acknowledge the particle pair and the tremendous number of particle pairs in each unit of Planck distance. Because
That's
without
one
that, we don't actually have an explanation for why the mass energy density or the angular momentum or the other various factors of that localized space has the properties that it does have. So we have to acknowledge that it has some properties that are very much like mass.
You're making an assumption that it has a property without interacting with anything else.
Well, we have various factors that are within already our very well recognized mathematics, like the local K of our space-time, the refractive index. We have our epsilon and mu. We have our
That's
G.
it. You hit on it.
You're misinterpreting what I'm saying based on your understanding.
Cosmological constant, the gravitational constant, these things have to be defined by something. There's got to be something there to define them. And that's what I'm saying.
Yes,
like,
there is. There is. And it should all be included in T mu nu. Everything, all stuff is in T mu nu. The vacuum energy is in T mu nu.
What? No, that's a cosmological constant that he brings in.
It can be added in there. T mu nu can have a constant.
Curvature and the Ritchie tensor. He also adds
T mu nu can have a constant added to it.
Lambda.
T mu nu can have a constant added to it. It doesn't have to be a separate entity. I'm saying that if you take away T mu nu, there is nothing. There's no particles popping in and out of existence. There is just a stage.
No. The quantum vacuum.
It has no matter. If there is no matter, there is no thing. If there is no thing, there's nothing.
No. I totally disagree with that. The quantum
you have to have a field, Sal. You have to have a field. The particles come from the field. The first entity you put in the vacuum is a field.
Look at Frank Wilczek's work and the idea of materiality of a vacuum.
I don't like Frank Wilczek's work, to be honest. I've read it. I don't agree with them. I'm more likely to agree with I can never remember his name. I'll think of it. Never mind.
I think the man is a genius and deserves another Nobel Prize. How's that? And I mean that.
It makes no sense to me, to be honest.
It makes total sense to me. As a matter of fact, the idea that they would take his axion and pervert it, and I'm totally against it. I think they should find the original axion, his axion, not this one Kathy Fries is looking at. She was on Brian Keating talking about it. Anyway.
Yeah. My point is that I look at it is that you have to start with a field. You don't start, the empty vacuum has no shape. It has no particles. You have to add a field before you have any pair creation. Before you have any particles, you have to add a field. And as soon as you add a field, it's not empty anymore. It's not space. It's not empty space. It's space filled with a field. You can't measure time until you have a particle that's moving to clock it.
What do you think time is, Todd? What do you think
time is? What you measure with a clock.
No.
I'll measure
physical time. What's physical time? Do you think, for example, physical time can have multiple dimensions like space could have multiple
nonsense.
No?
It's nonsense. What? Physical time is what you measure with a clock. That's all it is. There's no fourth dimension. There's no fourth dimension. Now is all that exists.
Todd, time is the expansion of the universe, basically.
Yeah.
That's really the best clock for time that we have.
Yeah. I don't believe
it's
in
an
the block
accelerated
universe, but the past
expansion.
still exists and the
It's an
future already
accelerated
exists
expansion,
and
so
everything
it
is
speaks to the
predetermined.
quality
I
of
don't buy
time
that.
as an energetic informational field.
Yeah,
Since we're dealing with an accelerated
that's a
expansion
clock.
of the universe. Yes, but it's a collective field. So what is it made out of? The things
Particles.
that are. I'm saying our understanding of physical time is inadequate. We should research
Our
this
understanding of physical time in general is very confused.
Mm.
Even among physicists in the mainstream. What one physicist says is time and another physicist calls time
Agreed. Like
completely different.
Carlo Rovelli thinks very different than Julian Barbour thinks very different than Lee Smolin. I do agree with
I
that.
take it down to the
It's
basics. Time is what I can measure with a clock.
Mm.
That's my observation.
Yeah,
I
but
can
that's
choose
your
any clock I
engineer's
want.
look to it. You have to step back and look at the fundamental of it. What is physical time?
I don't believe there is a physical time because I can't measure it.
You can measure heartbeats.
I think it has a lot to do with
That's a
entropy,
good
the state of
clock.
entropy, phase transition.
I have a great ticker right here.
You know, so you're saying basically, until you measure it, there is no time.
Exactly.
Oh,
Okay, I
Time is
understand
what you
that.
can
I understand.
measure.
I grasp that.
so
Well,
to you,
and
time is
just
an
to,
illusion.
If you
if I
can't
could,
measure it, it don't
To me, it's
exist. It has
physical.
no effect.
It's a physical entity. Lee Smolin agrees with that. Time is real. Julian Barbour and Carlo Rovelli believe in time is more of an illusion, an illusory entity. I believe Lee Smolin is correct. Time is very real. Physical time can not only be altered, it can be manipulated. But that's me. Eric Weinstein also believed in multiple dimensions of time, just like we have multiple spatial dimensions brought forth by string theory. One should not put down string theory because you disagree with the lack of experimental verification. Period.
I like
Okay,
string
because it looks to me like
It
Maldacena
leads to
came
conformal
upon
gravity, and that's what
experiment that was
I have as
performed in
conformal
1968.
gravity. So
Anyway, yeah, I mean, we agree to disagree. This is
well,
the
so
beauty of physics.
if I let me, so John mentioned time being related to the expansion of the universe. One thing I have wondered, I'm going to showcase how dumb I am right now, but
Nah, you're not dumb.
if the universe
You're not
is
dumb.
what the
Damn,
universe
you're,
is,
you're organizing this conference.
Then
well,
I'm a Sarfatti idiot.
the universe is one. The universe is like unity, right? The universe is one. Is the universe expanding, or is maybe the universe staying the same size and everything in it is becoming more detailed? Maybe losing energy and shrinking. Not shrinking. Shrinking is a bad word, but dissipating.
I believe
Becoming more
every
entropic.
unit is contracting.
I know I'm splitting hairs, but it's one of those paradigm changing. This occurred to me a while ago.
Oh no, and paradigms, concepts are extremely important. That's why
John,
the Superforce
mathematics says it could be either way, Tim, because if you look at the equation one way, the universe is expanding and everything else is staying the same size. If you look at the equation the other way, the universe is the same size, but we're observing it from a contracting galaxy, from a contracting.
Yeah, well, so maybe that contraction is the actual function of entropy.
Can't tell the difference. There's no measurement you can make to tell the difference.
I know. That's I'm.
Have you seen Roger Penrose's idea? Instead of inflation, what could birth the universe? Have you seen his cosmological theory?
Yeah, but I don't understand the connection between an absolutely everything's evaporated and there's nothing left, and then suddenly you've got a singularity to start a new one. I don't buy that. In Roger Penrose's cyclic universe,
Have you read
he ends up with nothing, and then there's a new singularity. Why?
Have you read Abai Ashtekar? He talked, okay, in this book, if you ever have a chance, get Conversations on Quantum Gravity by it's a compilation of conversations with greats like Nima, Juan Maldacena, Abai Ashtekar, right? By Jacques Armas. Read carefully the part, not only Juan Maldacena, but read Nima as well, but read Abai Ashtekar especially. The part on the quantum bounds. It is freaking pure genius. I think this is how it was done. And it talks directly to the superforce. You see, the quantum bounds has an analogy to supernovas. And let me explain. Can I explain why I'm saying this? Okay, and tell me if the physical mechanism makes sense to you. Please do, because this is important to me. As you well know, in a supernova, once the fuel runs out, it starts imploding. It comes to, say, on the order of 10 to the minus 15 meters. So we're talking about 1 femtometer. That's the realm of the strong nuclear force. It resides at 10 to the minus 15 meters. So we're talking about the strong nuclear force is there. Now, the densities we're talking about is on the order of 10 to the 14 grams per centimeter cube. So again, not exactly small, but not exactly Planckian either. So because of the strong nuclear force, there is a core bounce. It basically tells it tells the implosion, stop, you shall not go any further. This thing rebounds and it explodes, hence the supernova. Well, I'm saying there's an analogous mechanism with a superforce at the super density on the order of 10 to the 96 kilogram per meter cube. This contraction, it undergoes what Ashtekar calls quantum bounds. I call it an Ashtekar bounds. The whole idea is that the superforce at 10 to the minus 35 meters at the Planck scale tells the mechanism, you shall not go further. And again, this thing undergoes a quantum bounds, hence the formation of a new era, a new epoch of the possibly a new universe. But why not a super intelligence? Do you realize that most of our universe, you know, the work of Anthony Peratt, 99.999% of our universe is made out of plasma. Remember the Bussard ramjet, the whole idea of, you know, yes, you need huge scoops and all that, because again, the energy density is extremely low. It's on the order of 10 to the minus 9. It's not, you know, we talk about 120 order of magnitude difference between quantum field theory and general relativity as far as the vacuum energy density is concerned. Yes, it's true. But if it is plasma, check this out. Just hear me out. This sounds a little bit weird. But what if plasma under certain conditions has a capability of sentience, consciousness being activated on a macro scale? So basically the universe becoming a super intelligence, not an artificial super intelligence, but a natural super
That's
intelligence.
beyond my pay grade, man.
I'm just saying the possibility may exist. That's all. I'm just putting it out there.
Yeah.
So what I'm saying, I'm talking about something I call the triarchy of creation. Superforce based on the super density, which again is Planckian, because the superforce bridges the realms, and so superforce leading to super bang, leading to super intelligence. I call it the triarchy of creation. Just an idea. It's out there.
No, I was listening to Brian Greene and Sabina Hassenfelder telling me that the universe is deterministic, and I'm like, that doesn't even.
Well, in a way, if the super intelligence exists and it controls everything, yes, it is. It is deterministic. If such a super intelligence would, basically, this super intelligence would have the ability.
I binge watched Loki last night. You should watch it because that's what the end was.
No, that's
Loki is very intelligent.
Huh?
If we're talking about time, people should watch.
Loki!
He finally got what he wanted.
The Norse god, was he brother to Thor and all that? Odin.
Oh, yes.
No, he was the child of Odin with some giantess or something,
right? Yeah.
It goes off on a tangent and it goes into this. Basically, he does something that he's not supposed to do, and the time police arrest him, for creating a new timeline, and they're about to erase him, and then they use him to find another Loki who was off on another tangent, and it just becomes this whole time traveling
Bonanza.
Let me bring it back. Mark, let me bring it back to super intelligence because I think this is important. Let me bring about another analogy I've always wondered about, and let me throw it out there. The human brain supposedly contains on the order of 100 billion neurons, synapses and such. Our so-called observable universe has 100 billion galaxies, each with 100 billion stars in it. So again, this number, if you believe in the Dirac large number hypothesis, it's possible to make the analogy, what if this super intelligence is really a Boltzmann brain? You're acquainted with the Boltzmann brain. You know, Sean Carroll talks about it all the time, you know, as a popping. What I'm saying is, what if this super intelligence exists? What if this is what we're talking about? What if it reinvents itself with a quantum bound just to auto-experiment on new possibilities? I know this is wild speculation, but I'm saying what if? And it's all based on the state of plasma. What if plasma, under certain conditions, can become sentient?
Well, there are several authors.
As a working plasma physicist, I can tell you the plasma is sentient already.
Really? How would you?
It has a mind of its own, and you have to convince it to do what you want, but you can't try and force it.
Interesting. Very interesting.
There have been several authors that have hypothesized that. So, and I don't remember the name of it. Pete Gerritsen told me a book that he was really excited about.
Oh, Gerritsen, interesting guy.
Yeah, and he just finished a big book, and the idea in that book was, what if plasma filaments in galaxies?
Is it bigger than this? Is it bigger than this? Is it bigger than Roger Penrose's epic, in my opinion? The road to reality, 1,050 pages of absolute genius. This man should be lauded by King Charles III of England.
No, the road to reality is long.
If you ever
It's long. It's a long road.
If you ever listen to this podcast, please, Lord, yeah, absolutely, peerage all the way. This is a beautiful book. This is a must-have, along with a Superfluid Universe by Kirsten Huang and Carver Mead's Collective Electrodynamics. Unbelievable. Those 3 books, baby. I don't know what I have with the number 3. It is what it is. Anyway. Yeah. Okay, I'm done.
Yeah. Well, no, thank you. I mean, yeah, in terms of recording, so I would love to be able to put this up at APEC. You know, I'll edit. I will edit heavily. We'll probably end up with about an hour of usable footage, but that's okay.
Please make sure that whatever we say about mainstream physics is laudatory. We want them to engage with us, bro.
Yes.
We don't want them.
My comment to Brian Greene.
Definitely. No, we want them to start being more malleable, more, you know, like take us seriously. Right?
Why don't I?
So
why don't I stop? Let me stop recording now. I'm going to stop recording, and let me thank you guys both. And
I want to thank you.
Stop recording now.
Thank you for having us. Wonderful as usual. You have the absolute best interviews, bro. Listen, anybody that likes John Brandenburg and Salvatore Pais, please subscribe.
Sal, come on, Sal, you're the guy who invented the Superforce.
Nah, man, you invented gym theory. I mean, you gave life to the pointing vector. Everybody had forgotten about how important the pointing vector was. Anyway.
That's how I know there's a God, by the way, because he's a punster.
Okay.
The pointing vector points in the direction of the momentum flow, even though they're spelled different.
On that note, let me thank you. Let me thank you both guys, and Todd as well, and everyone, Jeremy Riss and Jeremiah Pop and Mark Sokol. Thank you guys.
Right. Live long and prosper.
Okay, there we go. So let me see. In fact, there he is, right on schedule, Mr. Sarfatti. Let me bring Jack in.
Okay,
Jack, welcome, sir.
All right, yeah. Let's make this short, sweet, and get to the point.
Okay.
So, do you have those questions? I mean, those talking points from David Grush.
You know what? Let me upload those slides, and hopefully I won't. Oops.
Well, if you could just speak them, and then I'll respond.
Oh, yeah. If you can give me 2 seconds, I will put them up. Sorry about that. Okay. Sorry. It's not going to do it as a PNG file, but let me see if it'll do that.
What could I? If I mean, do you have? Oh, well, maybe I could find it. I don't. I should find it too. Just
Actually, you know what? Here, let me do this. There we go. Okay, now it's sharing. Yeah, now it's sharing that.
I don't think people can read it easily, so you'll have to speak it.
Okay. There we go. Oh, and they can't see it, can they? Okay.
Yeah, so you're gonna have to speak. You're gonna have to read it. Okay.
Okay.
You read
so yeah, let me read the first one. I'll stop sharing. Okay. Yeah, I will stop sharing. So point number 1, I will just go through these then. That's a bummer because I have.
Okay. Let me make a preliminary statement so people understand the context.
Okay.
Okay. Preliminary statement is that I have been read into classified military material. Okay. Now you're going to just have to take my word for it because, like David Grush, I've given my word not to reveal my source, how I got the information, and you don't have to believe me. Okay. But I'm going to tell you what I think is the truth based on information, currently classified information that I shouldn't have gotten, but I have. All right. And since I've never signed, I'm not like Grush. I haven't signed anything. I've never signed anything. I could do anything I want. I'm a free agent. Okay. And the information I have would blow everybody out of the water in terms of what's going on in Washington. I mean, they're so stupid, So in any case, so take it or leave it. But I'm going to tell you what I know to the best of my knowledge that I would be willing to, testify under penalty of perjury to any, if I was subpoenaed, say, by the Senate or the Congress, everything I'm saying now, I would say under penalty of perjury. But I cannot reveal, I cannot reveal my source right now because people's lives would be endangered, like what Grush says. Okay. So that's it. Okay, so let's proceed from there.
Okay. And hopefully people can read this, and you know what? I can zoom in even further.
Yeah.
There we go. Look at that.
There we go. Yeah, but okay, but
that's too much. Okay.
Yeah.
So
state it anyway.
Yeah. So this is from Reddit. I'll just kind of preface this for the for all the audience folks here. So on Reddit it says the GRE Grush interview is Grush's best interview so far. Here are the key points they went through, and basically this was the Rogan interview, right? Joe Rogan, whatever his name is. So number 1 here, I'll highlight the number of retrieved crafts in the USA's possession is in the double digits.
Okay, I only know about 1.
Okay,
I know 1 for sure. Okay.
So then he said
what I can say about the one I know about. The one I know about for sure is totally consistent with what Philip Corso said in his book, The Day After Roswell. And it exactly corresponds to what Rick Doty calls the Cardinal 3. It's like 30 feet, weighs about 3,400 pounds. It's got 3 seats inside, all that stuff. All that stuff I can confirm, with very high degree of confidence, like 95% confidence, more than 99% confidence that the first-hand source of this intelligence to me is telling me the truth. And it's something that something that my source worked on, hands
Okay.
on. Okay, all right, okay, all right.
So let's go
I
down
know
number
it's
2.
one. Okay.
Events have been documented occurring since before the 1930s. So
Well,
and I
well, we know that. I mean, everybody knows that. That's no news to anybody, right? I mean, it goes
yeah.
back to the Bible. Okay, let's go on to the next one. Okay.
Okay. And Grush himself, I did see the interview. I watched the interview twice. Grush himself backpedaled on a few of these. Italy and Germany may have become allies during World War II due to events surrounding an Italian UAP retrieval.
Okay, I don't know whether that particular allegation is true or not, but what I do know with fairly high degree of confidence is that there was a crash during the Mussolini's time, and in fact, there's a lot of activity in that area, even today, and oddly enough, my cousin Margherita Sarfatti, at the time, was very close with Marconi, who ran the investigation for Mussolini at that time. So I don't know if they. I don't think that's why they became allies, and that's a much more complex issue.
Well, and again, even David Grush said may. He stressed may have, so he backpedaled a little on that, and that's fine, right? That's ancient history.
Yeah,
so.
but definitely, there was. I'm pretty sure that there was a Roswell type crash in Italy around 1933.
Okay, so let me see. And number 4, I think, is Lockheed Martin is in possession of retrieved UAPs.
Again, I have no direct knowledge one way or the other. I have no reason to doubt it, but let's go on.
Okay. Former Nevada Senator Harry Reid was aware of a UAP crash retrieval program.
Well, I don't have any direct knowledge about that, but that's kind of like, well known.
Yeah, well, and Harry Reid was very keen on this from what I've read. Let me see. Foreign intelligence agencies have breached our UAP reverse engineering programs.
I have no doubt about that.
You know what? I do a lot of defense interviews. Foreign intelligence agencies have breached our pretty much everything programs. I mean, there isn't much that, yeah. So let me see. So David Grush alludes to the USA's adversaries having their own UAP crash retrieval programs.
Yeah, that's for sure.
Okay. Well, that's notable.
Nobody's surprised by that.
Let me see. Grush says that USA is aware of other countries that are in possession of multiple craft.
Well, given the stupidity of some of the people who are in the government associated with this project, I'm not sure. But if they were confident and not stupid, I think the answer would be yes.
Okay. Let me see. Biden is aware of UAP crash retrieval programs.
I don't think Biden's aware of anything.
I was going to say, unless he forgot, he may have forgotten, right? That Reagan-esque memory, but
yeah.
Okay.
All right. Now this one I have. Okay. Now this one.
6-year UAP disclosure plan from 24 to 2030 is being considered right now as part of the Schumer amendment. And you had sent out an email. There's this back and forth on that. Maybe they will stop this. Maybe they're going to pull this, even though the NDAA 2024 was voted on. So
that's Steve Bassett. That's Steve Bassett worried about. But my position is not the same as Steve. My position is that this 6-year plan, and maybe it's a 10-year plan, this is basically the plan that Colonel, Carl Nell gave at Gary Nolan's Stanford, Soul Foundation thing the other day, and it's irrelevant. It's I make an analogy. It's like would you rather deal with the United States Post Office or with Amazon over your mail?
The post office is really nice where I live.
Oh yeah, well all right. But I'm making a joke,
Yeah,
but
I know. I'm
teasing. The thing is this. What I'm saying is that whenever the government tries to do anything, they usually don't do it very well.
Yeah.
Private industry does it better. And right now they're so behind. And I don't want to get too much into the personal details on it, but the point is that Colonel Nell I mean, I'm sure he's a nice man, but he's basing his assumptions. His assumptions are false. His premises are false. It's all based on the idea that they don't understand the technology. They don't understand what really what's going on. That's it, and they're hoping to enlist academics, and to figure it out. The point is, we have figured it out. We understand the basics of what's going on. We know where to look.
Yeah,
But
there's an information there's a, what would you call, a culture gap, right? There's a knowledge sharing gap.
I call it an intelligence gap.
Yeah,
But,
one hand doesn't know what the other hand is doing. Well,
yeah.
Okay, so let me.
The point is we don't need it. The point is the disclosure's already happened. Disclosure's come and gone. It's just that people people don't see what's in front of them. And,
Okay.
But the important point is that there are now private groups, and in some cases foreign groups like the Russians. I know the Russians invited me to Moscow. I didn't, but so the people are going ahead and working on this stuff, and there's even the Lorentz Livermore lab is testing my particular approach to it in their warp fusion reactor. So what the 6-year program is irrelevant. It's too little, too late, and it's not needed. Because we already know.
Let me go on to this one. Grush hints that Mike Rogers and Mike Turner are bought out by aerospace contractors and blocking UAP disclosure plan. And that's the Schumer amendment.
I don't know about that.
I don't know about that either. Some of this is pretty granular data.
Yeah.
Let me see. Grush is a proponent of disclosure and believes it will benefit reverse engineering efforts. That's
right? We're all on that page, right?
So Grush says that it is 100% certain that we're not alone in the universe.
Yeah, and so am I, of course. And I think, almost everybody here is already, that's preaching to the choir.
Yeah, I know. If you're watching this video, you probably agree. Let me see. Grush says this phenomena has been occurring for thousands of years.
Obviously, yes. We can get into some more detail on that if people have questions about that.
If I could interject, I mean, there are different approaches, right? Different people believe different things, but I think that this is one of the biggest paradigm changes is that not only has this been going on, but this has been going on for a very long time.
Oh, yeah. Yeah.
And I think that that's good. Like there are all these concerns about, people will panic, we're being invaded, or the world's, no, this has been going on possibly as long as the human race has been around, maybe longer. So nothing has changed. We're just becoming more aware, right?
Yeah.
Let me see. So, okay, next, Grush says the leading government and military officials refer to the beings as extraterrestrial in origin.
So,
big deal. Yeah. Well, I think that goes to so you have talked about time travelers. That's been something you've talked about, right? Which may or may not be from Earth in a different time. Hal Puthoff has talked about ultra terrestrials. So,
and Mike Masters, talks about
time travelers.
He calls them extra
temporals.
Extra temporals. Okay, but I got a direct contact with one that said it was from the future, and it predicted what was going to happen, which happened. So I know, I'm a contactee, right?
Yeah.
And they said, everything they said was going to happen is happening. So there we have it. What's happening there?
Now, another way to look at that too is if I was in the military, I'd just call them all extraterrestrial. It doesn't matter. I just, little green men.
Here's the thing. It's more. Okay. It's more than that because the physics says it has to be. Time. If you control gravity, then you control time. I mean, it's just physics. That's Einstein general relativity theory, and we can get into more detail how that works if people are interested. If we have time,
okay. But
let's go on the next question.
Okay, so Grush points to the idea that beings from retrieved craft may not have been sentient.
Well, again, that it depends what you mean by sentient consciousness, and that's physics. And remember that the Central Intelligence Agency 50 years ago recruited me and, Hal Puthoff, Russ Tugg, all these guys, that's some still around, to work on the two problems. One problem was, what is consciousness? That's what David Kaiser's book, How the Hippies Saved Physics, all about. What is consciousness? And how do the flying saucers work? Okay, and after 50 years, now we have a pretty good handle on it. We understand both aspects of the phenomenon. The high strain. The one good thing Eric Davis has done with Jacques Vallée is the paper that he wrote with Jacques, on the high strangeness paper. That based on the Skinwalker Ranch. That's good stuff. Yeah. And also what Hal Puthoff recently wrote about, with the extra dimensional, his general outline. That's all. Yeah, that's all correct. I agree with all that.
Okay, so let me go here. People in government tried to destroy Grush's image when he attempted to whistleblow on the secret government reverse engineering program.
Yeah, well, we know that's true, but that's politics. That's
yeah.
That's
and then someone leaked his medical records as well, which I can't. I don't know. That must be that's a HIPAA violation. That's an enormous penalty. So, let me see. Government entities destroyed one of Grush's colleagues' careers as a show of force after targeting Grush.
Yeah, well, I don't know about that, of course.
I don't know about that either. Let me see. On 2 occasions, individuals of unknown origin explained to Grush and his wife they could touch them at any time, which is clearly an allusion to violence.
Yeah. Well, again, I have no reason to doubt what Grush would say about that.
Yeah,
that doesn't surprise me.
Let me see. Grush stated that other publicly well-known officials got similar threats at the same time he did.
Well, again, we have reason to disbelieve him. Why, I don't have any, I don't have any personal intelligence about that.
Yeah, I can't speak to that. Let me see. The Atomic Energy Act of 1954 is the origin to all NHI information being classified.
Yes, and this is important. This connects with me personally because remember my professors built the atomic bomb. My professors were the A team for Oppenheimer. Hans Bethe, Phil Morrison, and Robert Wilson, all these guys. So, and I was a student, an undergraduate student at Cornell, only like 10 years after the bomb. I got to Cornell in 1956. So 11 years.
Well,
after.
And from what I have heard, and I could be mistaken about this, but the classification for this is under the DOE, right? Because it's nuclear related or something along those lines.
Yes, and again, I don't have any, really, direct knowledge of that, but it's no accident that I was recruited into this whole program as a kid, basically, and sent to Cornell where all these nuclear guys were. Okay, I mean, I was there. I was helping Phil Morrison cleaning his office. I was an undergraduate when he was writing the paper with Cocconi on contacting extraterrestrial intelligence, with the 21 centimeter line. Okay.
Well, let me go down to this next one. He says that UAP craft emit nuclear energy. That's not a very precise description.
Okay, but now I can explain that now. See,
okay. Yeah.
Okay. The way that is, that is, of course, most people, they don't understand the physics enough. Yeah. That's a signature of warp drive. That's warp drive. That's gravity. That's time travel.
Because so you're talking about red shifting, blue shifting, right?
That's the blue shift.
Yeah.
That's the blue shift. In order to get the lift, the repulsion, the anti-gravity creates a blue shift. The blue shift will ionize radiation and cause radiation sickness, like what allegedly happened at the Skinwalker Ranch. Travis Taylor himself says he got sick from it. Okay. And that's what when Kit Green, the CIA guy, doctor, gave all that blood information to Gary Nolan to analyze. Those are all military guys who've gotten too close and have been exposed to the anti-gravity blue shift, which, by the way, Jack, I'm the one who predicted that. I'm the one who explained that. Nobody
Yeah.
else.
Well, and these are conventional. And again, for people who don't know your work, there probably aren't many because your work is very prolific. You've been doing it forever. Again, you are one. For people who don't know, you are one of the top experts in UAP physics, right? You're like the guy. So, in terms of the physics,
Is
for
there
this,
someone else? Who's that?
well, I just I don't want to stroke your ego too much.
I'm joking.
But but so yeah, I mean, these are relativistic effects. You've predicted this. Another one that I think you agreed with was in the Puerto Rico video, there was what appeared to be gravitational lensing, right?
Yeah, and
Which
we
is
picked it
also
all. That's the shape shifting.
the shape shifting, right? Many people have reported that gravitational lensing. If you're modifying gravity to that extent, you're likely to have these effects.
Yeah.
Let me
So
see.
that's all. So these are all markers of warp drive, and warp drive means time travel, by the way. Okay, and there's one other thing: the reverse Doppler. Yeah, you know that if a warp craft is coming toward you, you're going to see more like instead of the Doppler motional blue shift, you'll see an anomaly that looks redder than it should be, and likewise the other way around. So that's an easy signature. That's an easy thing for them to measure.
Yeah.
Just observing the frequency spectra of these machines in motion, and you can easily tell if it's warp drive by the anomalous frequency shifts. I mean, that shouldn't be difficult to do. They probably already, hopefully, they have this kind of information, but it's classified. But in any case, I predicted it just from Einstein's general theory of relativity. It's not.
Yeah, no, I'm completely there. Everyone that I know who studied the physics on this is completely there with you. So let me see. Let's go down. Grush claims that senior officials in government tested the waters, quote unquote, with the populace in the past to gauge public perception of the phenomena, but never had a plan for disclosure.
Well, he's probably right, but we know. I mean, this goes back to H.G. Wells, not H.G. Wells, to Orson Welles in 1939 or
War of the Worlds, right?
Yeah, all that stuff.
Well, but what is testing now? So there was the Spielberg movie, Close Encounters. There was that claim. I'm hoping that was the test and not Independence Day. Independence Day would not be the right test. So.
Well, I don't know. Well, here's the point. All of the above. Here's the general point that people have to understand. The physics of warp drive, time travel, paranormal, telepathy, all that stuff, the physics is pretty elementary. That means that any civilization anywhere in the universe, if they manage to get to a certain point, are going to discover this technology. So this basically, as soon as they discover relativity and quantum theory, you're basically almost there. It's just a matter of 50 years, maybe 100 years. So there are many different groups out there. It is like Star Wars, there are many different groups. I used to kind of laugh. What was it? Some of these guys, I forget their names, saying there are all these different types of ETs. Well, actually, that's true. I know from my classified briefings, I know there are at least 3 different ones. There are 3. I know 3 for sure.
Okay.
3 different ones.
Let me go down here.
Friendly. Wait, not all of them are friendly. We have a problem, Houston. We have a problem. Okay.
Let me go down here to the next one. We can return to this because we've got some extra time, I think. So the government is in possession of multiple different types of biologics as well as multiple different types of crafts. This goes to what you were saying. Okay.
Yeah, this goes to what I'm saying. And it depends what government are we talking about. I'm not going to say what government we're talking about.
Okay. There's cliffhanger.
Which I can't say. I'd say governments, yes.
Okay, governments.
And the answer is I mean, I know. I have some intel on that. I can't give too much detail, but the answer is basically yes.
Well, I mean, this is just speculation, but Thor, the gentleman who did UAP theory, who was talking gravitational lensing, one of the points that he made was, he said, if the universe is full of life, as the Drake equation suggests, if it has multiple civilizations, as you've said, they can probably travel faster than light, travel through time. Earth right now, the developmental stages that humanity is going through is probably one of the most interesting places in the universe, right?
Yeah,
There's
yeah.
it wouldn't be a surprise that everybody would be here just seeing what's going on.
Yeah.
So,
And also, there's the Hastings, the guy, Robert Hastings, all the stuff with the nukes.
yes.
Yeah. And it's no accident that I'm involved in this, because my professors built the nuclear bombs, right? And so it's no accident that they were also into UFOs. And it's no accident that I was recruited, into this project many years ago. I've been working on this for a long time. This is and it's all now happening.
Yeah.
It's all
So
coming.
let me go to the next one. I think we have 4 left. So this is number 4. Okay. Grush describes the topic of interaction between humans and non-human intelligence as an area he can't discuss in great detail, but hints at the idea it could have taken place. So this,
it's taking place. Of course, it's taking.
well, I almost wonder if he's referring to that famed there was supposed to be some meeting or treaty in the Eisenhower years, right?
Oh, I don't know. Well, maybe, yeah. I'm sure. Yeah,
Some
I
form,
don't doubt. I don't doubt any of that. I mean, I think there's probably all that is probably true, but I have information on that sort of thing, very detailed information on that sort of thing, which I can't go into detail on. But the answer is yes, and it's a lot stranger and than you think. Then I can. Let's see what I can say without. The high strangeness aspect.
Okay.
Is very much part of it.
Okay. I won't.
No, but I can. All this stuff that Russell Targ, the remote viewing, that put off, all that stuff is all real. Psychokinesis, the Uri Geller stuff, that's all very much part of the UFO phenomenon. And I have a lot of details of which I can't get into, but it's very. The paranormal, with the paranormal part of this thing, that's the part that will probably scare a lot of people.
And actually, if I could interject for a moment, I did in my interview series, right, several hundred experts on various fields, and when it comes to UAP, that is one of the most consistent things. I did an interview with Gary Nolan, and he reported it, and the thing that caught me was he said, "Why is that happening?" He's like, "I have no clue, but it is." But what's interesting about that is you have like yourself has reported it, Dr. Eric Davis, Dr. Hal Puthoff, Dr. Gary Nolan. This is a consistent report. Is some kind
also
of
John Ramirez, CI John and Jim Simivan.
Yeah.
See, they're all and Rick Doty. Rick Doty also, So this part of it, the mind control part. Okay, there was there's the 2 slides I keep putting up on the internet. There's now 6 observables. That's the hardware, the nuts and bolts, right? The warp drive, the time travel, the mechanics. But there's also slide 9 about mind control.
Yeah.
Okay.
Yeah.
The paranormal, the high strangeness.
And I should mention for the audience that you added an observable. There were 5. Luis Elizondo ATIP had 5. You added 1, and I forgot what the 6th
I forgot
was,
exactly. I think Julian Gaffrey is the one who actually did it. But yes, that refers to Travis Taylor saying he's getting, that's the blue shift, the anti-gravity blue shift.
Yeah.
That's the stuff that Kit Green has given to Gary Nolan, to the blood of all the, like the Havana syndrome type symptoms. That's the ionization, that's the radiation sickness, basically from the blue shift, from the warp drive.
So let me go down here. Grush states that recorded documentation of non-human intelligence goes, quote unquote, pretty far back in history.
Yeah, well, of course, yes.
Yeah, and I'm seeing stuff online now, paintings, right? That they've been there forever, but yeah. So it's pretty far back there. Grush wouldn't be surprised if humans were genetically engineered.
Well, I would say almost for sure. I'm like 90% certain we were. See, that's also one reason why they're here. But the whole Garden of Eden myth, well, what that was, it's like maybe 6,000, 10,000, whatever. It wasn't that long ago. That the time travelers from our future came down and took us, some our ancestors, and did some CRISPR genetic tweaking of the DNA code, and because suddenly there's writing. When did writing appear? Was it 6,000, 10,000? When did all that happen? It happened fairly recently, right?
Yeah. I don't know what the time scale.
There are these discontinuous changes that really cannot be understood in terms of ordinary random Darwinian natural selection, and that's intervention. We have all the technology now. We could do it. We almost do it. I mean, they're doing it at Stanford and all that. I mean, Gary Nolan could do it, right?
Yeah. No. So I had asked Gary about that, and what he'd said was, if there was obvious genetic tampering, it would have been detected by the many, 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 gene scanning technologies that are out there. But in some ways, I felt like that begs the question, because number one, in some ways you have to be looking for it to find it, and in other ways, like for instance, hybridization modifies the genome, leaving no. There are ways that it could be done that wouldn't be obvious. There may be different ways of doing it that are less obvious. So I didn't feel like he had
a. That's interesting, but have they actually tried to look? Have they taken fossils?
I don't think they have. I don't think they have.
Yeah, they haven't. If you don't look, you're not going to see it, right? But
exactly, yeah.
But also Gary himself was talking about this, this thing that the high functioning have this kind of, I forgot, there's this part of the brain where there's a lot of complexity that most people don't have, and I heard Gary Nolan call it a genetic mutation. It's probably a genetically engineered mutation. So the point is, I don't think there's any question about that.
Okay.
My own view. That's my own view. That we're genetically engineered.
And then our final question of the day, David Grush claims remote viewing is real, and that it might be related to certain evolutionary traits in the brain that some people possess, which is exactly what you just said.
Yeah, well, that's what Gary's talking about. And the point is this, that we understand now the mechanism of consciousness. We understand it, and generally speaking, we understand the physical mechanism. It's not difficult. That's part of the project that the CIA asked me to work on, right? What is conscious? How these things fly? That we understand the quantum mechanics of it. And to the point now that we can start making sentient machines, artificial intelligence that has the same consciousness we have by simply imitating, using the hammer-off stuff, the microtubules, making these nanoscale quantum dot artificial neural nets and pumping them into what are called further condensates, and then that's what we are. We understand that we're conscious, okay? And so all that is coming, and it's going to come very quick, I think, very fast. Unless we have a nuclear war, of course.
Yeah, so let me very quickly, while I am sharing, I'm going to put that up there. This, I believe, is the interview. Joe Rogan, sorry for forgetting his first name earlier. I do listen occasionally. So I believe this is the interview that they're talking about. And I will put a link to this in chat. And then now what I'll do is take this down. Now, Jack, do you want to bring Mark and the guys in and go over this more in detail?
If somebody has questions, I'll
let's do that. Okay, so I'm going to take that down. And you know what? We should at least give Jack a hand. Dr. Salvatore Pais and that's the wrong me here. There we go. Okay, sorry about that.
Okay,
I have the guys here. Everybody, please give Dr. Jack Sarfatti an applause.
Yeah. All right. Well, let's just get to the question. Does anybody have any?
Do you guys have any questions for Jack? Okay, and I'm pasting this.
I have a question. Could you go into a little greater depth on the most recent thing that you guys were just talking about on the consciousness side of things, and what your research or experience in the past has suggested?
Well, okay. Well, if you just go on my Twitter, I always there's a paper now by, what's his name? The Finnish guy, Paavo Pilkin. He's written a review paper. He's an eminent cognitive scientist in Helsinki and Sweden. And he's written a review paper in December of 2022, about a year ago, called, it's on my website. I mean, just look up, what is it? The brain as a quantum measuring device. And in that review paper, section 7, he describes what I've done in a accessible way. You know, if you're not a physicist, it's for other psychologists, you know, people. And he describes, without the math, the quantum mechanics of consciousness that we've discovered. It basically takes off from the Hameroff microtubule theory. It's not quite the same, you know. It's not really Penrose's gravity theory, but there's there's a precise mechanism, okay, which I predict explains consciousness, and which can be tested because we can build machines now, nanoscale artificial neural nets that will have the same kind of consciousness that we have. But of course, that's also a function of the input sensors and the output motors that they have. But you know, we're talking. It's pretty interesting. You see, this gets into Sam Altman. You know, the Jack. By the way, Sam Altman is my next door neighbor. Here, he lives next door to me. I haven't met him yet because
he got rehired. They brought him back.
Yes,
they brought him.
Yes. And so he's literally, we have a common boundary here. I mean, he's right in the next building that he owns. But he's hardly there, and I'm in London a lot, and Italy a lot of the time. So, but in any case, if you read about, there's this woman, Pippa Malgrim. She's on Substack. I met her in London, and she's written a very interesting analysis of what's been happening with Sam and his business and everything. But apparently, Sam is getting into all this. He's getting into robots. He's actually going to be competing with Elon Musk and all this, you know. And so he's going to eventually, once he be very interested in conscious AI, because that's the next step. The next step for, you know, all the artificial intelligence now is not conscious, and you can make it conscious. It's like Frankenstein. It's alive. It's conscious. Okay, you can make it conscious by changing the hardware. It's a hardware problem. And I basically know how to do it. You know, in principle, I know how to do it. So,
yeah. So there you go. Well, on that note, I mean, if that answers the question, I wonder if we should move on to lab time then.
And is that it?
I think that was it. And you know, and Jack, I'll take that section of this and put it up on the YouTube channel as its own breakaway.
Yeah,
too,
please.
Okay. Well, Jack, let me thank you so much, and you're more than welcome to stick around. We're going to go to lab.
No, I got stuff I got to do.
Okay. Well, thank you again. It was definitely an honor and a pleasure again, sir.
Okay. Bye. How do I do?
Okay, so lab time. Can I start with Drew in sunny Florida, who has been very patient? Does that work, guys?
Hey, Tim.
Hey, I'll go to solo layout and then, oops, how does this work? There we go. Okay. Yeah. Do you have updates for us? Go for it, sir.
Yes. It's been a very busy couple of weeks here. Now that I've figured out what's going on with this whole build the world's worst capacitor, I have built a couple of really bad capacitors that have generated some positive thrust. What I'll do is I'll share a sanitized version of my tests from whenever the 21st was, a couple of days ago. Let's see here. Can I just present? Share screen. Screen sharing. Share screen. Working on it. Technology hates me.
No worries. You're doing great. And this is StreamYard. It's a little different. Yeah, there it is. Let me see.
Okay.
Add to stage. There. Perfect.
Okay. Well, can y'all see, I don't know where the blue thing is, the stop sharing thing? It's in a real, oh, okay. I can move that. Good. Sorry. Just had to move that out of the way because the cool stuff's down here at the bottom. Basically, this particular test generated 4.4 millinewtons of thrust. As you can see, it took 20,000 seconds to charge the system. Working on that. That's a little excessive even for me. That means I have to sit out there for 20,000 seconds and keep the temperatures all stable so that all the sensors. It's the bane of being poor. You can't afford temperature compensated vacuum sensors. So 4,400 micronewtons is the equivalent of 449 milligrams of force, if you will. If you were looking at a scale, 4,400 micronewtons would be equivalent to 449 milligrams of mass at 1G. 449 milligrams divided by 360, which is what these little plates weigh, is 1.25 Earth unity thrust to weight ratio. Yay, past unity. The cool thing about this is it was run, this is like the 4th in the series of tests. 102 means it's the 2nd day, and I ran the crap out of it the day before. But anyhow, there was still somewhere in the neighborhood of 1,000 to 2,000 micronewtons worth of thrust trapped in the system, because it takes forever for these things to charge down, to bleed off, because I don't give them any opportunity to do so. So if you take the low end, it would have been somewhere in the zone of around 1.25. If you believe that there's trapped charge in the system, as I do, then I could have had up to 1.81 Earth unity in the system, which ain't bad out of a piece of, well, we'll just call it saran wrap. That's it. That's all I got. The impulse engine is very close, gentlemen. Very, very close. Oh, and Ivo launched, and I hope their spaceship blows up.
So, Drew, question for you if I can. You've been, eking your way up, and now you finally hit Unity. Now you're past Unity. For each of these improvements you've made, it's been getting better and better, but you got to be reaching some theoretical threshold there. How much more runway do you think you got for improvement?
Well, Charlie tells me that 4,400 micronewtons for basically 10 square inches is pretty much the edge of the envelope. His math says that's it. I mean, we have this super elegant formula now, and you plug in field and area and all kinds of nonsense, some of the parameters of the materials and stuff, and boop, out pops an actual number now. And we've been hitting it pretty serious. We're within a few percent pretty much on every run. So we're probably hitting that asymptote that you're talking about. I don't see getting more than about 2 Earth unity, because as you can see, the way down here, it asymptotes out. It flat lines out. There really wasn't any thrust generated from, say, 17,000 seconds to whatever that is, 22,000 seconds or something. So, I think I'm there.
One other question for you. If you had all the resources available, and would it even work to have a atmospheric lifting device, right? If you had enough of these panels to be able to lift themselves, plus the power supply and other necessary equipment, is that even feasible to do in atmosphere at STP and all that?
No comment.
Well, I love no comment. I'll take that how I want.
You should take it positively.
Yes.
If resources are very soon to not be a problem.
If that was the case, would it have to be just absolutely massive, or would it be possible for it to be a reasonable size?
It would have to be pretty big. The problem we're running into is this is material unity. Okay, so this is, let's say let's say I get to 1.25 across the structure. Okay, and I'm an engineer. I'm a mechanical engineer, so I understand how things are built. So let's say I have 1,000 pounds of propulsive material. So 1,000 pounds of propulsive material means I have about 250 pounds of lift above the weight of the propulsion material. That means I have to pack everything, the structure that can handle all this. Because remember, this stuff still weighs something. You're just producing a thrust source. So you're hanging a balloon above a gondola that weighs, 1,000 pounds. Well, you got the weight of the balloon, you got the weight of the structure, you got the weight of the cables, the guidance, the control system, the battery, whatever the hell you got in there. So this thing would have to be fairly large in order to self-launch, let's say something crazy like a small U-16 satellite from your backyard. It would have to be, fairly large. It would have to be something on the order of a U-16.
And timeline. What's your timeline looking like?
No comment.
Okay.
But thought y'all'd like to see it.
Yeah, Drew, that is awesome, man. That is awesome. Thank you.
Way to go, man.
Yeah, that is seriously cool. Okay, well, Drew, thank you, sir. Who is our next victim on Wheel of Lab Updates? Mr. Salvatore.
Yes, we got a couple stuff. Actually, Jeremiah Pop was down here at the lab for 10 days. He left just on Friday early morning. But I do have some videos to show you guys of what we were working on. And with me for a moment, I do have to upload it right now. And there's some sort of issue. If we upload these videos while the thing is going on, yeah, it just pops up right away.
There we go.
So I'm going to pause this for a moment, just explain to everyone what this is. We're calling this the Tavares drive. Harold Tavares, one of our own APEC members, has recommended a rotating magnet disc. So this is a disc made out of G10. Kind of looks like jade, so we're calling it the Jade Spinner. It has 24 magnets in it, very powerful magnets, and then there's 2 stator magnets that are stationary that are mounted on top. You can see them over here. I don't know if you guys can see my cursor, but there's 2 very powerful magnets over there, and the magnets are rotating through it, and that's supposed to create some sort of force. We did see a force, but we'll show you a control test after.
You ready to spin it? All right, here we go.
So you can see a laser dot on the bottom. That indicates how much deflection this device has. Air currents definitely play a role. This thing is producing lots of airflow, but it is sort of symmetrical, and we'll get to that in a moment. This is with the magnets installed. Later, we're going to do a control without the stationary magnets, but the same setup.
5,000, 300, 55, 37, 6,000, 7,000, sorry, 6,100. 8.6, 9.1. I'm not max. 12.02.
So the laser is like roughly hanging on the edge of that little counterweight there.
1.7K. 9.6, 9.8, 10K.
Now we're doing the same thing without the stator magnets. So this should be a control test, and we're seeing a very similar effect.
12K. Here we go.
That's pretty well built, Mark. Pretty well built machine.
13.1K.
You guys did a great job.
Yeah, so we did do a great job. Thank you. I agree with that. It was very well built. I have had accidents with past rotating magnet devices where they flew apart. This one is very, very well built. and we did not see. We saw some effect. We did see some thrust, but in our control test, it seems like it was just air current that was playing, most of the role in that as well. There's one other experiment that we ran, and this one was suggested by a girl that you might all know, Amy Eskridge. So in this video, we have the Jade spinner facing the North Star. The force measurement over here is coming off of this gauge on top, and it's, according to their theory, the spin coupling force should either increase or decrease the weight of the object as it rotates. Turn down the volume a bit. We have another version of it where we flip the disc around. I didn't see any conclusive results over here. I just jumped through it. There's the raw data. It's settling in between. Then we start floating direction. No real obvious thrust was detected with this device. But there are still a couple variations that we want to try. We want to try the magnets instead of facing at the stator magnets, instead of them being axially oriented, we want them to be oriented away from the axle. And Jeremiah actually took this device back with him to Milwaukee, where we're going to be working on it further to do some more tests.
Hey, Mark, question on that. For these force measurement tests, did you happen to have RPM measurements going simultaneously so you could see if there was any weird harmonics there?
There was harmonics when we had the stator magnets attached. Yeah, that's just when it would vibrate more. And that had to do with the design of the device and how rigid it was, and how the magnets would shake, and at what point would you amplify sound. But there was harmonic points, and they would just muddle up your numbers. They would either shake the laser or ruin our force gauge numbers. But as you can see, just jumping around over here, there was no obvious thrust being created. And this, again, the axis of this rotation is pointed at the North Star, which is based on Richard Eskridge's paper. He just apparently discovered some sort of force, the spin couple force, that when rotating magnets facing the North Star, you would either see an attraction or repulsion. And in this test, we did not detect anything with the equipment that we're using over here. So you can see the results right here. It is shaking a lot, so the numbers aren't perfectly steady, but that's what we ended up with. And Sean Logan over here just joined us at the lab, and hopefully we'll have some updates for you guys on the next open mic. He has a really cool antenna. It kind of looks like something out of Star Wars, and we're going to be hitting that with a 1,000,000-volt March generator. See what that can do.
Is there any way you could show that device on camera?
Unfortunately, I don't think my USB cable is long enough to make it. I can give it a shot, though. Let me see. We have it hung up right now.
Well, Mark, I'm just blown away by the quality of I mean, that thing went, what was it, 12,000 RPM? Something like that?
Yeah, it went up to about like 13,000. You could
okay.
It's hanging down over there on orange straps. We call it the phi antenna. It's basically, he's using the golden ratio of phi, 1.61, and has a series of concentric rings that make up this ring antenna. Sean, you want to explain to them what it is?
Maybe I could show you a picture.
Here, sit down.
Yeah, it's I gave a talk on the open mic on the 11th about this.
It's a set of concentric steel cylinders. And they all have equal mass and surface area. And you charge the central one negatively and then vary the charge on that so that the Coulomb potential in the space around and within the central tube varies with respect to time. And the geometry of the outer rings sort of acts the way like the position of your fingers acts when you're fretting a guitar. Different arrangements of rings fret different chords. Is there a way to show a picture?
Only if it's on the computer already and ready to go. No. I think that's it for us.
Did Jeremiah get a chance to look at that device and get some ideas on it?
Yeah, he saw it. We actually built spacers for it so that it can go on its side, and right now it's hanging on its side. So yeah, but we didn't get a chance to actually try energizing it or anything like that. There just wasn't enough time.
Awesome. Well, thank you, Mark. That's super awesome. Let me see. You know what? If it's okay, let me go to Isaiah. Isaiah, welcome back. Do you have lab updates for us?
Hey, good afternoon. I have probably a few of them. Hi, everybody. So I'm working on, I think it's a generation 5. It's a pulsar electromagnet for the rollers on the stator ring for the SEG. This is it. It's the biggest one I've made so far. Has around 21,600 winds total on both coils. I was winding some other additional coils on the Gen 3 device, and the whole idea came to me at once. So I just went up and built it. So I'm working on these, doing tests, and it's looking very promising. What else? Put together 4 different sizes of rings. I'm going to be placing an order here probably the next month. Magnetic rings. We're going to be running tests, me and Jared, and slowly working together eventually for like an AC/DC magnetizer system. But those are kind of things that are in the works right now. Right now, I'm just let's see. The next step to really getting the 1, 2, 3, 4 Gen 4 SEG replica working is just the copper ring and assembling the rollers, and then perform the tests of how high RPM I can get on it. So yeah, those are my updates. Not a ton, but making progress every single day. I'm working on it.
Being the last guy on the planet that actually doesn't know what a Searl effect generator is, could you have like a 30-second version of what it is?
I could plug it in actually.
I'm assuming it's a propulsion system.
What I'm doing is just for. I wish there was a way I could flip this camera around. What I'm doing is mainly for energy, but the inventor originally said it could be used for propulsion, and he claims he had it worked as an anti-inversion gravity device. Got it off here first. So turn this around. Some of you have seen this, others have not. This is a Generation 3 device I'm working on, and basically you just have 4 elements. You have supposed to be neodymium Teflon as a dielectric, a magnetic layer, and then copper. This is awkward for me because I'm using the selfie camera. And then you have, these are called rollers, and there's 12 of them for the first main stator. Basically, they orbit around the stator, and I'm trying to get a velocity of about 500 to 600 RPM before we think something might happen with it, generating electricity. Right now, it's just powered by 12 volts at about 2 amps. So this is just the demo device. This one here does about, well, when the right battery's in, it does about 237 RPM. These are like 2nd generation electromagnets I have running it. This one's going slow. I think the battery is just about dead. So I use a rechargeable Milwaukee battery. I have temperature gauges here for the coils, and the center core. What I'm working on here right now, slowly upgrading, is the generation 4. I think it is. I lose count with the new generations. Generation 4 device. This inner core is 34% neodymium, and then you have your Teflon. I have the magnetic rings. It's just not. It's not in place yet, and the copper ring has to be assembled. But these are, I think, a generation 3 electromagnet. So as you can see here, the new one is quite a bit larger than these original magnets, electromagnets. So the whole thing I'm getting towards is higher RPMs to be able to really get anything interesting coming out of it. If the neodymium will start to cool down, is one of the effects we're hoping for. Yeah, it's basically a way to take energy out of the environment and put it to a coherent form that you could use to run appliances or whatever, charge batteries, that kind of thing.
Thanks.
Okay, awesome. Isaiah, thank you so much. Let me bring Curtis in. Curtis has a lab update too, and then we're going to have to do an applause for all of you guys at the end of it, because you are all kicking serious butt. Well, here, we'll do an applause for all of you guys now. This is like amazing lab updates today. Amazing lab updates. Thank all of you. I can, from the bottom of my heart, thank all of you. Curtis, what do you have for us, sir?
So I'm in the lab. The pump's on right now. I'll shut it off. So basically, this is the vacuum chamber here. You can see the piping. So basically, to shut it off, I just need to close that. Let me do that real quick. So there's 2 pumps. There's a turbo pump as well, and you can hear it kind of whining there, but it's not as noisy. And you can see the gauge here kind of jumped up. Pressure was a lot lower, but once you turn off the pump, it climbs back up. So I'm just going to block this in and turn off the turbo pump. Okay. That will start winding down on its own. So, and I did upload a presentation. I can go through that. Anyway, that's a look at and then there's a camera that we use, and then the test articles in there. You guys can see that.
Oh, it's exactly the same kind of test setup I was trying to build.
Yep. So let's see here. Present. Here we go. Did that work? Yeah, the turbo pump takes time to wind down, so there'll be a little squealing as it relaxes. Can you guys see the screen there, the slides?
Yeah, and Curtis, I brought everybody else back in too on the side. So
okay, sounds good.
Yeah.
So lab update. Oh, there we go.
Oh, there we go. Okay.
So yeah, we got a new gauge in. The other gauge that was there, I try to do a calibration, but you really need a reference.
Oh.
So we got a new gauge in, and it was about one or so millitors above the old gauge. I mean the new gauge. So that's good news. So we're actually measuring higher pressures than what we really had, at least recently. So the new gauge is in. The turbo pump is piped up, and we've gotten below a millitor, which was kind of the goal. We're hoping to get even lower than that, but the system really needs to off gas for a while for us to get that. Especially, Jim likes this. It's like a composite chamber that was put together. The ends, you can see that how thick that glass is. I think that was like a bulletproof thing that they made years and years ago. So it's an interesting setup, but it's not a standard vacuum chamber where you have metal and things. Things can be cleaned off and go down really quickly. So there's off gassing that needs to happen. But I think we're in the regime where it's less likely that we're having effects from the air. And as I said last time, if you try to do this experiment because you have piezoelectric stack vibrating, you will be pushing air. In fact, there was a council simulation that was done where basically it was shown that you can get like newtons of force from the air at certain frequencies, at resonance frequencies. So that's definitely not not something that we want to have in the system. This is an example of a recent run. I think this is November 19th. I can't see okay, there we go. Let me maximize my screen as well. So basically the way you read this is, has the date, and it shows the voltage of 0.7. So what that means is on the function generator, we're setting a 700 millivolts peak to peak, and it's actually going through a amplifier, and from there's a voltage. Basically, we're increasing the voltage using a coil with some turns. So by the time the voltage gets in there, it's a lot higher. But anyway, that's the settings. And you see the 44 to 24 kilohertz, that's a sweep downwards, and in 10 seconds, basically. And the 90 ramped is the waveform. Basically, it's a sawtooth wave with 10% up and 90% down. And 2.3 millitorr, that's the pressure it was at. So the traces here, the way that are described here, the red is the torsion arm moving, and then that aqua trace that starts below, that's actually the test article. So if you guys recall when I showed the test article there briefly, there's a little dot on a couple dots on it. One is on the actual stack, so that we could see when the stack moves, the test article moves and it's pushing the torsion arm, we can see that that this data is being taken from that video with the tracker, looking at that dot and seeing where that is moving with reference to the camera. So you can see what happens here initially. There's a spike up where the article will move, and you'll see the red go down. Now the red is the torsion arm moving. Now, if the torsion arm moves the opposite direction, that's a kind of an action-reaction effect, right? But what you'll notice is that the torsion arm goes a certain distance, and while the article is still pushing, it will start being pushed by the test article. So initially, it looks like there might be some stick slip with the bearings and a action-reaction, but then the test article will continue to push, and you'll get the whole torsion arm moving that direction. And so there's places where it looks like there's action-reaction, like standard Newtonian effects going on, and places where the Mach effect looks like it might be happening, or it could be the air still. I don't know. Now, the next slide here has that more explicitly shown, where you can see here the red going down, and I guess I will call that turquoise going up, and that's clearly looks like an action-reaction effect. But then afterwards, the test article is maintaining that push, and so you can see the torsion arm starting to come back and get pushed for a time. And down here, this is seconds. So it does look like we're getting brief pulses of the run. And I have a link here to a video. I don't know if I can play that, or if that's something that if I have to share my screen to do that.
I think that if you share the window that it's in, if you bring that up in a new window, you could do it.
Okay, let's see here. Let me bring that up. Okay. Pause it.
That might be the fastest way. Otherwise, you'd have to download it and re-upload it.
Share screen. Okay, share screen. And then
Yeah, and then it'll make you select the window that the video is in. And that's probably your Google Drive, right?
that is. I'm on one monitor right now.
Oh, there we go. There,
So you guys
oh,
can see
oops. Oops, hang on. There. Oh, yeah, there we. I think that's it. No.
Yeah, I'll mute
Okay,
that.
it's showing the wrong window though.
Okay, let's see here. Stop. It's in. Share screen. Entire screen. Okay, entire screen is an option. There we go.
Okay.
I'll do that. Can you guys see it now?
Nope.
Nope. Okay.
We could hear the device whining in the background.
Yeah, that's the turbo pump winding down. Let me try it one more time. Chrome tab. Okay. Select it. It's not showing up. Safari. Okay. Share Safari. Okay. Now, can you guys see? Can you guys see the video?
Nope.
No.
No, look, it looks like it's not.
It's not wanting it, huh? Okay.
Yeah. It could be because you're in Safari. That might be what's.
Yeah, the other tab. Let me just Google.
Yeah, and we maybe give it one more try, and if it doesn't work.
Yeah. And then okay.
Yeah, but Curtis, I appreciate you giving us the update on it. This is awesome. These results are amazing, man. All of you guys are kicking serious butt today. This is like.
Sorry about that whine. I can't.
Hey, Mark.
Okay, here we go.
I'll trade you shirts.
Oh, yes, we will.
Okay. Send me a 3XL and let me know what size you are.
Okay.
Wait, here we go. Okay, okay. There we go.
You guys can see it?
Yeah.
Okay.
Oh, yeah.
So now this is a 10-second, similar to what we saw earlier. And here, what you're seeing, this gold, this is a basically it's a kind of like an accelerometer that's in the stack. And so the higher that goes, the more vibrational energy is happening. And what this is without tracker. So we have to actually process the video to get that tracker. So this was data from today, so that's not processed. But the red shows you like the motion, like how long it actually, moved. And that's the red is the torsion arm moving. So now down here, this is the fast Fourier transfer. So basically, the way we look at it is when we're looking at the different resonances, and the different harmonics here, what we're looking for is for the second harmonic to be higher than the first. So if I go back further in the video, you'll notice that, this really starts to take off and vibrate or actually increase here when that peaks. So that's what you want to watch out for. So you see that peaking there, and then the gold goes up, and it stays like that. The second harmonic stays higher for a time, and that's when it really pushes forward. So this is like basically going through runs, and you guys can see the video on the right. The thing will, like, when it gets to the harmonic, you'll see it actually start to move and push to the right. And then the torsion arm here, it'll maybe slightly bump left, but then also push to the right. So the red is not reflecting this, but you guys can see the article itself and how much it really, does move in there. This is one of the better.
Is this like Mach effect or something?
This is the Mach effect, yes.
So I vaguely understand it. You're basically pushing and then what? Shrinking the mass, and then there's less rebound or something, so you end up with a net force in one direction. Is that the dream?
So what this device has is it has a brass reaction mass here, and on the other side there's like a thin aluminum plate. So what's happening is that as you're vibrating, sorry for that whine, I can't slow it down. As you're vibrating, maybe if I do this, as you're vibrating, you're actually pushing on one mass when you have more versus the other mass. So if you push preferentially one way when you're like heavier versus the other, you'll get a in the theory anyway, you'll get
How are you heavier?
some motion.
How do you go from less mass to more mass?
Well, in the theory, when you're putting in the energy, you're increasing the differential mass of the matter in the article. So basically, you can consider it the stress energy tensor, because you have more energy in there, and that's when you're pushing the right way. And when you have less
So
energy,
basically, when it's charged up, it weighs more.
that kind of thing. I mean, it's worked out in Jim's theory, and it's not the stuff that's out there, you know, in his books and in the published literature. It's all that stuff is based on, you know, standard general relativity and the models that he uses to derive it. The models of matter. So, you know, if you guys recall, I gave a talk on Mendel Sachs's the quaternion formulation of general relativity and what that implies. Jim is not using any of that stuff. So, just to be clear on that.
That is awesome. That is awesome.
Oh,
Well,
cool.
guys, let's do this for lab updates. I think. Well, you know, I should let me check real quick and see if Jared, do you have any lab updates for us?
I do, but I had a question for Curtis first.
Okay, yeah.
On your Woodward device, so the material properties are really important for this asymmetric damping, right? So I assume that you guys have gone through and you've optimized the materials, or you think there's more room for optimization of those materials to like increase the difference between squishy and hard?
Yeah, so I've been asking about, hey, why can't we let's use tungsten on one side and aluminum on the other, because tungsten is like almost as heavy as brass is to aluminum, is, you know, tungsten is to to brass. So it's tricky because, like you said, the thickness of that reaction mass and the material properties, like how fast sound moves through there, apparently all affect this. So before I got on the project, really, like, you know, being heavily involved, I got on 2 years ago. Before that, while they were doing those NIAC grants, the NIAC 1 and NIAC 2 grants that they worked through, they actually optimized this test article. So it is what it is today. So before, there were different mountings for it, and a lot of that, they found a lot of the practices they were using before were dampening the effect. Now, one of the problems that happened, though, is that the team convinced themselves that having air in there didn't make a difference, and it turns out it does. So that's one of the things, like I mentioned last time. Anybody that wants to do this, you really want to do this in a vacuum, in a good hard vacuum, because even a millitor or two, you know, like I mentioned last time, there's a helicopter on Mars, right? Who would have thought? So so you want to really get below the regime where the air can carry the vibrational energy and push against, and, you know, the device.
Second question for you. So material properties change under different stimuli, right? So if you have a very highly electrically charged piece of metal, it's going to have a different speed of sound in it than a completely uncharged piece of metal. Have you guys played around with trying to have any of the components be at very high charge?
So I wouldn't say the voltages are, I would call them low voltage, being an engineer, right? For me, medium voltage is like 4.8 kilovolts. so I mean, this is maybe in the hundreds, or a couple hundred or less volts on there. And what I would say about the voltages, I mean, really what's going on is in the piezo material. That's really where the effects is happening, where you're getting charges kind of put in there and taken out really quickly as the thing is expanding and contracting. So you have a mechanical motion along with a huge, change in the voltage and the electrical energy in the stack. I would say that the masses on the ends, the effects of those have more to do with whether when you get the vibration, right, because you're pushing on that metal, whether the acoustical properties of the metal and the size and shape of it will dampen the vibrations that you're trying to have with the piezoelectric stack. So basically, when we take a test article, it's tested for its electric resonance and I would call it an electrodynamic resonance, because you have mechanical resonance and at different frequencies, and that's what kind of is reflected in that and the Fourier transform. So really, when you make an article, it's unique, right? Because it has its own specific size. We do, there was an optimization where they figured out how long to make the brass end caps, and they went through different links and found out, okay, there's an optimization for that, for example. So that's the extent of how the metal is optimized. So I would say this is using low voltage compared to a Tesla coil or something that's way higher.
Excellent, thank you.
Awesome.
So I got an update.
Yeah, Jared, give us your update, and then after that, we'll go to open discussion.
So the first presenter was talking about Lorentz force thrusters. So that's actually what I've been working on for the last month or so. Is I got some of these devices that I've printed out. So I've got these square magnets, like these guys, right? And they're super strong, N52s. And I got 2 on one and then 2 on another there. And I run the wire through there and I run current through it. But what makes it special is that on the sides, on the vertical sides here, where it goes up, and down on the sides just outside the magnets, I got magnetic shielding material that ends up redirecting some of these magnetic fields. So you can turn on and off the capability of that material using high frequency RF, which is how you can try to eventually get some asymmetric damping in there. I've tried multiple iterations of this. MATLAB calculations are a lie. They tell you 100x of what you're actually going to get. And part of the reason for that is because this is a Newton's law abiding citizen. The right hand or left hand rule, whichever way you're looking at the thing. When you apply the current to it, yes, the wire is getting a force in one direction. But the problem is that the magnets are getting an equal and opposite force in the other direction. So sure, you can put all the calculations into it you want, saying you're going to get 10 newtons of thrust, but you're going to be getting under 0.1 newtons of actual thrust because equal and opposite, right? The only way to actually achieve something is through asymmetric damping or pulsing of this thing in special ways. So this is my version 2.0 here, where I have just one continuous winding all the way around. I tried a version 3.0 where I wanted to be able to pulse on and off in different polarities, each of these. So I wound each of these individually. This one ended up, I tried doing just one as a test, and I was getting absolutely no deflection out of this thing, which made me go back to the version 2.0. So now I got a version 2.1 that I'm printing right now. So instead of 8 pairs of magnets, which this one only has 4 pairs, instead of that, I filled all of these spaces in between. So it's going to be magnets all the way around, with the wire doing this the whole way around. and the magnetic shielding material in between each of those pairs. I have one short video to show. So there's a very simple version of this that anybody can test. You can see it hanging up here right now. That is just a spool of 26 gauge wire. I took an Allen wrench and I put a bunch of magnets, bunch of little disc magnets all around that Allen wrench and put it down the throat of the spool. So north is facing all inwards. And then on the outside of the spool, I did the same polarity with a bunch more magnets. So it's got a magnetic field around it of north inwards. And then on the inside, it's got a magnetic field of north inwards. And you run a current through it. And the idea is you should be getting some Lorentz forces. If you have power going to this thing, the current is going to make those wires twist, not what you want. You want this thing to be standalone. So I got a little circuit here that's a little battery hanging from the thing, and then some very thin wires going to a switch down here so I can turn it on and off at a distance. And because these wires are at a milliamp, you're not getting any deflection there. I've got a laser pointer up here so that when I turn it on and off, I can see what's going on. The cool part is, this is the main feature of my lab update. The cool part is that I ended up hooking up my signal generator to the switch so that I could pulse this thing on and off at different frequencies and see if I could get any kind of better deflections out of it. And for this particular one, I got at 2 hertz, I got this wobbling deflection. And at 7.5 hertz, I got a much smaller deflection, but much faster. So it's acting kind of like a speaker or something like that. This thing doesn't have any magnetic shielding material in it, though, which is kind of the secret sauce. Is you got to be able to redirect magnetic fields to make this thing work. Yeah, rather than show the video, I think I've already described it. At 2 hertz, the laser pointer goes like this. At 7 hertz, it goes like that. That is my update for now. Is I am trying to verify or nullify Lorentz force thrusters, and I think that I'm about halfway to 2/3 of the way there.
Awesome, Jared. Thank you. Thank all of you guys. I want everybody to give an enormous applause for our lab presenters. You guys have been kicking butt. I mean, today actually, I feel like this is one of our best conferences. We had great presentations, and then you guys just blew it away with lab updates. So thank you all. I mean it. I mean, Mark and I were talking earlier this week, and like you guys you have inherited this massive legacy. You're keeping the boat floating, so to speak. You're keeping the dream alive,
Okay, so everybody is working on impulse drive. Who's working on warp drive? All of us are building impulse drives in one way or another.
Got any dilithium sitting around?
Now, I'm telling you, man, I got the impulse engine working. I need
Mark's working on a warp drive. Mark?
Yeah, we're kind of working on warp drive here.
Yeah? You're going to wrap a bubble around something and we'll be able to zip?
Well, we're trying to make a bubble inside of something first.
Okay.
Wait, cool. There's Jeremiah. Jeremiah, can you turn your camera on?
Sean's device might actually act kind of like a Star Trek warp drive, because Star Trek's warp drive does like this nested field thing. Each one of the nestings of the field is equal to a warp factor, and his device is kind of doing the same thing with the nesting.
Sean's device looks like a warp drive from Star Trek. It actually looks like it.
Well, and then the SEG.
What does Sean's device look like?
Rings within rings within rings.
Yeah, but they get longer and longer and longer. Yeah.
The cylinders, the longer and longer cylinders, and
yeah. And the spacing is very important. Apparently, they're all like sympathetically vibrated, right? Or something like that.
Do you guys want to see the schematics? I could put it in the chat.
That would be cool.
I want to see it work. Go for it. I'm telling you guys, I need a warp bubble. If Tim would turn off the record, I'd show you something very cool. I can't have it recorded.
Why don't we can wait, when we decide to close things down.
I will stick around for that, Drew.
Yeah, I came in at the end because when I'm falling asleep in my chair, and 2, I have to see the secret sauce after party.
I need more coffee too. You guys wear me out.
Oh, coffee! That's
so much enthusiasm, so much excitement. I found this stuff called Death Wish coffee. They have it at Costco now. Has like twice the caffeine.
So this is it. This is the device. This is a schematic of it at least. Sean, you want to give him an explanation?
If you go on YouTube and look at the APEC open mic for November 11th, I gave a whole talk about this.
Yeah, it's just the last one on the channel. I can find
That's
it
what
for
it
you
looks like.
guys.
Yeah, it's been painted, but that's essentially it.
Okay, so can we get the 30-second version? I mean, you put electricity in, RF in, and then it forms a bubble around itself or something?
You vary the charge on the central tube, the long skinny one in the middle. You want to charge it negative and then make it more and less negative really fast.
Sean, I'm dropping the link into chat right now. Oh,
Okay.
that's private chat. Hang on. Now I will drop it into public chat.
Okay, so let's see. If you vary the voltage or charge level, you're going to build an asymmetrical capacitor. Is there a ground somewhere? Are any of those rings grounded?
No, those are the outer anything.
So they're not attached to each other, and they're metal.
Yep.
Yeah, that means they're all going to polarize to the same voltage, basically. Okay, so let's say this thing works. What does it do? Does it pull itself forwards, or does it form a little bubble in space or something?
My hypothesis is that you're gonna get a corkscrew shaped beam of energy coming out of the pointy end of the thing. Like a helical kind of beam of stuff coming out of this, and it's something similar to a magnetic field, but more fundamental.
And Sean, you'd mentioned something about that cloud busting. Was there any twist in that cloud busting?
It made a hole in the clouds once, or at least a very strange hole appeared in the clouds after I was testing it inside of a Faraday cage. No, I don't think it was twisting. It was just a perfect circle of blue sky in an otherwise overcast sky. And then actually, I forgot to mention the next day, some people I knew who worked at that, it was at a marina, it was inside a shipping container at a marina. They said, yeah, I saw some really weird hole in the clouds yesterday. And I said, yeah, that circle of blue sky. And they said, no, we saw square holes in the clouds.
And can you estimate how high the clouds were and how large the hole was?
It was really big. It was so big that the harbor master came running up to me and grabbed me and started pointing at the sky, which was real uncharacteristic of him to act that way.
And was it low overcast, medium, high overcast, high altitude overcast?
It was it looked like a sheet of really flat clouds, like just very uniform and flat, and I that seems like something you normally see when they're high up there, but I don't know how high they were. That's what the coolant potential looks like around the pipe.
Yeah, you guys, lab updates this week. You guys are just blowing it away.
Yeah, I wish I understood electricity.
Well, anyway, does anybody else have something to share?
you know, I think that's it.
I guess I'll just give a
Again, we
brief
should.
mention of this last point since you asked, Drew. So there are a few people working on warp drives. So I just had a brainchild of a thought earlier today, called up my ham radio buddies.
Hold on, Jeremiah. Why don't we officially go to open discussion first?
Oh, that's a great idea.
Yeah. Now, so we'll be officially in open discussion. I'll put my open discussion, and let me thank everybody for making this an amazing conference so far.
And we'd like to thank you, Tim, for setting it all up and running it.
Well, thank you as well. I'm sorry for a little bit of the bumps along the road. We had a changeout. Hugh wanted to go early, and then that changed our schedule, and then Jack bumped in at the last minute, but we made it work. So,
Jeremiah, can you turn on your camera?
Okay, I'm gonna get some coffee.
I'm gonna look like I'm dying here, but I suppose just for you guys, I'm still running the same 3 hours of sleep that I had the night before that plane trip, and I have not been able to catch sleep since. So I'm still going after all this time. I'm dying right here. Anyways, yeah. So I had a phone call with Adam Space Case earlier. He has a lot of skills and experience with ham radio equipment, high power transmission, multimeter bands, and electromagnetics in general. So we put our minds together and came up with a very basic proof of principle concept that should be pretty easy to build for a tractor beam style high frequency panel. So you guys, some of you may remember my universal AC attractor panel. It basically just is a series of parallel strips that all run side by side, and you have alternating between any two strips potentials, scalar potentials, positive and negative. So we're not really dealing with like antenna transmission structure here, just really high electric potentials switching place at a very high speed. The closer the strips are next to each other, the tighter the field is on the surface. So if these two strips, say, were an inch apart, you could imagine that they'll form an inch-wide circle in diameter, which will be a half inch above and a half inch below. So that's the effective area of this device. Well, what we came up with was using a series of split-ring Yagi arrays to push that field, sort of like a Hallback array, way out to one side and intersect them at an angle. So we have this quote-unquote bearded energy bottle style interference zone. And of course, the waves can't directly interact because photons aren't going to couple with each other, but they will couple with the refractive index, 3 epsilon mu. So we're hoping that it will work as well as my little versions that operate at lower frequencies on the 2 meter band, and that should generate enough force to universally attract every material towards the antenna. Also in vacuum, so we're looking forward to that experiment. I'm looking forward to sleep. Anyone else have anything to say?
So Jeremiah, that tractor beam stuff that you're talking about, what power levels are we talking?
When I tested it, I was only running a few watts, and I was able to pick up things like 1/8-inch thick panel glass, every kind of plastic I tried, small pieces of very flat metal. The only problem with the old drive is that the surface interaction was so tight up on that ribbon cable. In order to get any kind of good capacitive coupling, you have to be right up on it. And now what we're trying to do is increase that from a few watts to almost 1,000 watts and increase that range from 0.5 millimeter to several inches, which actually puts it into the useful category of tractor beam tech.
And how focused are we talking? I mean, it's electric field, so it's just spherical, or you got it directed somehow?
Yeah, instead of just using a plain old folded array, we're going to be using a Yagi style ring array. And we're going to just do parallel driving. So just imagine it like a really big split ring resonator, but stacked.
So is it like grabbing stuff with electrostatics?
It's grabbing stuff with electrodynamics. I got away from calling it electrostatics because it gives the wrong idea that you can produce the universal attraction force that's like a gravity simulation with just a DC high potential. In this case, it's absolutely dependent on the volts per meter changing. So this is a dynamic phenomenon. It requires a high frequency alternating voltage. And this really is not about the current at all, because no current actually enters or leaves any of the artifacts that are being attracted towards it. They're just capacitively coupled in the dielectric field, radiating off the surface of the parallel line array. And in this case, we're not going to use that parallel line array. It's not the most effective design.
So you're creating an AC electric gradient, and anything that's on the other end of that gradient is getting polarized, so it gets pulled in.
Right. Basically, anything where the speed of light is slower through it than it is through free space will get sucked towards the gradient. Which is everything that exists in the matter world.
Attraction?
Go ahead. What's that?
How is that not electrostatic attraction?
Because it's not static. The electrostatic refers to a condition in which the potential is not changing over time. That's what makes it static. Static means not moving. This is electrodynamic, meaning that the potential must be changing over time for any effect to occur.
Okay, so, but...
It's just a matter of terming. It operates by the way that your brain is probably thinking it does. It just simply isn't the right term to use, calling it static.
Okay, but either way,
otherwise, I think
cool
you
attraction.
understand. What's that?
Is what you built, are you saying it's a bunch of concentric full-wave loop antennas?
That's what we're going to be doing. Loop antennas arranged in a Yagi-style array with at least 3 elements each. I figure we could probably do 4, just a quadrature set as a minimum test artifact, but ideally it'd be better to go with something more like 9 or maybe 5, maybe 20.
So they're not all in the same plane. They're kind of.
We wanted to be able to flex the plane to curve it into a sort of parabolic interference zone and see if we could affect the range where we actually get the greatest coherence. What would really be sweet, though, and the ultimate goal with the high-frequency transmitter is if we just consider the wavelength for a 2-meter band and we can wrap that sucker up tight enough, then we have a pretty good idea about our volts per meter. And if we create an interference zone where it actually traps something out at a distance but does not want to bring it closer to the array because the field intensity would actually be dropping because the array is physically large but the interference zone is small, that means it would act kind of like laser tweezers but for super long wavelengths. And instead of particles being trapped, it would just be anything in there with a different refractive index in free space would be pulled towards the interference zone. So you could push and pull with the device if it works out the way we think it will. And that would be really cool.
Have you ever heard of I think he was Russian, but he lived in France. There's a guy back in the 20s named Georges Lakovsky, and he made something very similar to what you're describing.
I don't know about him, but I'll bet you it's probably almost identical to what I'm describing here. And looking at his work, I'll probably just, have a good laugh about how it's already been invented before by like 10 other people before we ever got to it. We're never the first. If somebody else, I can always go back in history and find somebody else that did something so similar, it might as well just be the same thing. I haven't seen an original idea pop out in a super long time from anybody.
Jeremiah, can you turn on your camera, please?
Like I said, I'm really tired, so I prefer not. Is it really necessary, Mark?
Thank you.
I'm dying over here.
Okay.
We all are.
Yeah, I got mine. It has been a long day, and this is Thanksgiving weekend, and this is APEC's 3rd birthday. So let's give an applause to APEC. We survived 3 years. And I was talking to Mark earlier this week. I mean, we've kind of inherited the legacy of like the high frequency gravity wave conference, and then there was STAFE and the SPCIF conference that Glenn Robertson did. There's Jack Sarfatti's Cortona conference, the Sarfatti science seminars that kind of come and go. We've kind of become the community center for all of those. And I mentioned to Mark earlier in chat, I reached out to a bunch of past conference presenters from the other ones to try and get them engaged. I don't have to tell you guys, we're losing folks left and right, just from old age. People worry about conspiracies, but old age does more than anything else. So,
well, it doesn't have anything to do with old age, but we went. A group of us crazies went together and we watched that Ancient Aliens live show where all 5 of the guys show up and then they talk for an hour and a half. Okay, if you haven't seen it, it's worth the $50 to go get the ticket and the $8 a beer. Um, we're talking 5,000 rabid, crazy, we want to believe crazy people, and 5 or 6 of the panelists down there and talking and stuff. It was the coolest hour and a half I've ever spent in a theater. So there are an endless number of people who actually believe all this stuff. Okay, they want the aliens to be real. They want the spaceships to be real. They want this dude with the big hair. I don't know. They want him to be real.
He is real.
I gotta tell you, the dude who stole the show was that Travis guy off of Skinwalker Ranch. When he showed up, he got a standing applaud. All he did was he was like in flip flops. It was amazing. So.
Well, some of that I've seen a couple episodes of Skinwalker. Some of that seems like it's the one that used to get me was Ghost Hunters, and Skinwalker reminds me of that sometimes, right? Like they're down in the tunnel and they're like, the thermal camera shows this as being cold, and and the one guy's like, aren't there water pipes? No, it's a ghost.
Actually, Falcon Space was originally set to be a part of Skinwalker Ranch. We signed the NDA, and they read me in on the whole project, and it sounded like a ghost hunting expedition. And I said I didn't want to have any part in it. Actually, in hindsight, there is something going on there that's a little more exciting than ghost hunting. I have been to one of those Ancient Alien Live things as well. I bought tickets last minute, and I ended up getting the seats in the front row, smack center, for like dirt cheap. And there were like diehard fans there, super excited about it. But they're just repeating the same thing over and over again. It's
fun to listen to.
Yeah,
it's fun to see the energy in the crowd. I mean, there's 5,000 rabid, crazy people that want the aliens. They want to go and they want to like squeeze an alien or something. I don't know.
It must be all those implants in one location.
Well, there's a lot of ancient astronaut theorists out there, and I for one am one of them. I came to anti-gravity research from realizing that Judaism was alien worship, and all these other religions are the same thing. Ancient Aliens doesn't touch those touchy subjects. They look at the Zoroastrian, they look at the older stuff, and say, oh, that was aliens, that was ancient astronauts. But they don't want to touch the really touchy subjects, which is the Bible, the New and Old Testament, the Quran. These are all alien worshiping books.
Okay.
There you go. Well, guys, we have about 10 minutes left, right? I think we'll shut things down at 5. This has been an amazing conference session. This has been an amazing conference. So I cannot thank you guys enough. And it is so cool to see everything moving forward, just like one session after the next. I mean, we've got amazing presenters, and then just to see you guys pushing these projects forward, And Mark, that wheel that you had, I was terrified when that spun up. I was sure that thing was going to explode. And
I was in the room. I was actually terrified.
So Mark, for the and Jeremiah, for those spin tests where you did the control experiment and the not control experiment, you kind of touched on it. Was there any noticeable difference between the two? Like, is there even a 1% extra deflection?
The problem was, without the stator magnets, the motor draw is actually lower. Energy is going somewhere into these magnets, and if it's not eddy currents, which the draw is way too high for eddy currents versus the complete and total lack of heating happening in either the stator or the rotor, we have to figure out where the energy is actually being dumped into and why the motor load is increased by almost 7-fold with those stators in place. So the RPMs were different, 12,500 versus a little over 14K, and so the deflection was different because the RPMs were not the same. So that's a problem.
One other question on it, if I can. So that center bolt that you got there, you got this magnetic field that's spinning and is all around there. Yeah,
it's aluminum.
So you'll get eddy current. You'll get a change in the magnetic field if there were magnets versus no magnets in that center axis.
Well, not in the center axis because the stator is way over here.
What about the Earth's magnetic
I mean,
field?
it's way too far away to induce any kind of eddy currents in a small cross-sectional diameter aluminum rotor.
What
What I'm concerned about is that the interaction between the stator magnets may be experiencing eddy currents from the edge interaction at the rotor.
Those tiny little magnets that are spinning around, they're about half a Tesla. They're really powerful.
They're
Yeah,
stupid
what
strong.
do
You
you
can
think
hear
it'd
it,
be
I mean.
the Earth's magnetic field? Do you think it'd be interfering with that? I mean,
We
because they're
consider-
really powerful magnets, right? They're spinning really fast. Do you think that could be creating drag on it?
The whole idea about the Earth's magnetic field, same with Helmholtz coils, is that if you place a magnet, no matter what its shape, between a magnetic field where it's completely uniform, it's not going to have a propulsive force in any direction or the other. What it will do is align to the magnetic field, but it won't actually have any pull because there's no gradient. And we consider that the Earth's field at any given point is so uniform that we effectively don't have that force. So we would expect it to maybe tilt in alignment with the Earth's field when the motor is running because there's current flowing through it at that point. But otherwise, there shouldn't be any kind of significant difference just because of rotation on the rotor magnets, the permanent magnet side, between powered and not powered.
And we've seen that effect with the Banduric test because the stator magnets of a rotating outrunner motor would align with Earth's magnetic field, and you'd see like a sticking point in the pendulum as it went past that.
It was surprising too. That whole like magnet floating point torsion pendulum, man, that thing was so stupid sensitive. We got that thing tuned in perfectly. I did not expect such an incredible response from a motor that had roughly about 200 milliamps flowing through it to pull so strongly like a compass. But it does. So
the reason why I was asking earlier about the potential resonances and now about the changing magnetic field around the thing, using just one of these little nifty magnetic field, trackers.
I just gave Mark one of those a couple days ago.
Yeah, so freaking useful. So if you mapped,
Absolutely.
where I'm going with this is if you mapped the field with this thing, and you were to test it at these weird resonance points, you might be able to observe if there was any aspects of it that wasn't just mechanical, or thermal or other weird stuff. You might be having some weird magnetic resonance effects that this thing might be able to show, like, oh, look, I got this weird bump in this spot now that I didn't have before.
Well, that's why we brought it back to Milwaukee to test. So while we were out there, Mark designed the CAD on these in no time flat, and we cut a bunch of them on the CNC. So we've got more of these insert blocks, and you have 3 different magnetic field orientations. We've only tested one of them. So right now we have north on one face, south on the other. You see my little south arrow on the bottom there. The stator magnets are arranged the same way, except for in opposition to the rotor, so it self-centers. But as you can see, they're not actually directly over the top. So these fields are technically not in alignment. There's actually an orthogonal interaction from the edge because everything past that point on the stators here, both top and bottom, is in a very tight loop at the edge of the gradient. So we're actually getting a slightly orthogonal, perhaps 45-degree field interaction coming off the edge of these, the field flux from the stators. And so we're going to flip them with this being north and south on the other side. So we're going to flip them with the north facing towards the center of the shaft on the top and south on the bottom. And then we're going to flip them so that north is facing forward on top magnet. And actually it would be the same. North on the bottom would all be facing forward. So that'll kind of pinch it together too and unify the forces. That way we don't have any torquing or twisting of the disc. So there are 3 different configurations. Like I said, we only tested the one, and we haven't really screwed with position all too much, and we only tested it in hanging orientation like this. We haven't tested it like this to check its interaction with the magnetic field of the Earth or any of the other things that still, for a good due diligence analysis of this drive, we would have to go through the iterations and verify any changes. Like the first version was this little thing, and it's convenient. It's nice because 1, it's shielded. 2, it's got this little optical trigger on the top. Just shine a flashlight in there and it'll spin up. And it's got its on-built laser right on the bottom and an onboard battery pack too. So like this thing just goes on the 4-point pendulum. Everything is on board, and it gives you a pretty honest test, which is not anything close to impressive with restricted airflows and whatnot as far as this drive goes. But it at least does produce enough of a counter torque continuously where it gets kind of curious, asking oneself, where does this counter torque come from? And where is the energy being dumped into that's causing load on the motor when we don't see any heating of any components? So these are mysteries that I think if we can answer them, we can redirect that lost energy into a vector force.
I can totally attest to the strength of those square magnets that you guys got. They are almost impossible to pull apart sideways like that. They are the strongest little magnets I think I've ever had.
That's K&J Magnetics for y'all. The magnets that you get on Amazon are junk compared to what you get from K&J Magnetics.
By the way, let me just give a public apology to Richard. He was going to meet us down at the lab. He drove out, and I guess I don't think I knew about it, and I think Mark and I were both totally distracted. It was kind of a chaos week, so I wanted to apologize to you, Richard, publicly here for the sake that you drove out 2 hours to the lab and there was nobody there to meet you. So we are sorry for that. Please forgive us.
Yep. Thank you very much, Jeremiah, for that. I forgot. Yeah, Richard, sorry about that. Jeremiah, do you plan on putting a airflow shield on it?
I'd like to stick the whole thing in a vacuum chamber. I might finish it up with the various configurations, and if I can't fit it in my vacuum chamber, I'll just ship it back up so you can run it in yours.
Yeah. Well, while we're still recording, we got about 5 minutes left. Let me thank all of you guys, and thank everybody who's watching, and thank everybody who's participated in just making this a community center. I mean, it is amazing, and when you look back, like what we've accomplished is just remarkable. It's remarkable, and it's like the best is yet to come. And I could say that definitively because you guys are like halfway through constructing all these incredible, amazing devices.
This is the Thanksgiving APEC. I'm thankful for APEC.
We're all still digesting dinner and all these ideas, but despite the perhaps appearance of lower energy, I promise you all our brains are doing the same things that they always do inside. We just aren't showing it with the bodies yet.
There's a lot. There's so much going on right now, right? I mean, the research, all of these projects are moving forward. There's results going on. This larger thing, the UAP story, there's stuff that's kind of moving forward. Right now, it's kind of like in that holiday lull, but it's all kind of under the surface currents.
I wanted to mention one small thing. Because I've been running tests like 6, 8, 12 hours now. And the other day I noticed that the sun was out, which, this time of the year in Florida, it's usually cloudy. And it dawned on me to walk over to the power meter to the house and check to see which direction the money was flowing. And it was flowing into the house. So I've got a 15 kilowatt solar array, and it's enough to run the entire house, plus twice as much. Anyhow, the point I'm making is, for about 8 solid hours, I was running a warp drive engine on sunlight because I was making more power than FPL was. I was actually selling power to FPL. And it occurred to me that might be the first green warp drive on the planet. Because, I was over Unity. So by definition, I was, as far as I can tell, I was waiting for the aliens to come down and say, okay, you figured it out. Here's your free ride to the space station. And it was operating on 100% solar energy. It's not right now. It's actually it's running right now.
So the power company was actually paying you for the privilege of testing the work.
It never quite works out that way. You always end up paying them. Curiously
Just
enough,
less.
Yeah, you just pay them less. But you never get away with less than $35 a month. So you're always paying at least $1 a day for the convenience of selling them electricity, which is bizarre. But it struck me as odd that this might be the first instance of a green warp drive on the whole planet, and maybe the last. Who knows?
Well done, sir. Well done.
I think it's the first of many. The first of many. So. Well, guys, I think we're just about at the top of the hour. Do you guys have any final thoughts for today before we close things down?
Yeah, but none of them I can share on the recorded line.
Yeah, well, okay. Why don't we do this then? It is 4:59 Pacific. I think we're just about there. Let me thank everyone. Again, this has been APEC's 3rd birthday. I'm humbled and honored and overjoyed to see this conference grow and see everything it's doing. And again, to see all of the progress that you guys are doing is absolutely remarkable. you know, and again, just to finish that thought, I mean, APEC has become the community center. It is taking on this legacy role for all of these past conferences and innovators that came before us. And it's just wonderful to see this continuing on. So on that note, I'm going to close things down, but have a wonderful Thanksgiving weekend, guys. And we will do something in December as well. We're still figuring out the schedule for that. Over and out.
Long and prosper.